go to a current slide. There it is. Before we get started, let's just go over what's happening. Okay. We had, last time, we finished topic 9, which was on solids, what was it about? Fluids and solids. Did I give you the test on that chapter? Okay. So if you didn't get that before you leave today. We also did the lab for that chapter. The downside of that was I didn't have a chance to type up the lab, so basically everybody did it on notebook paper. So if you weren't here for the lab, you'll need to get with somebody and get the data from them and get the raw data, and you do the calculations, okay? I think you'll be able to hear most of everything on the YouTube video. So you'll need to get the data and then do the YouTube videos. Now, I think that brings us up to date with labs and tests. And here's a little timeout there. Well, let me finish this up. So today we're going to start on topic 10, get as far as we can. If we finish in time, we may actually start the lab. I doubt if we'll finish that soon. So we'll probably go straight through with topic 10 today. And then on Monday, we will, if we need to, we'll finish topic 10 and then do the lab on 10. I will return all your work to you except the research papers. So time out on the research papers, since that's come up. I think last time exactly half of you had turned in the research papers. That means half of you have not turned in the research papers. So I need those. If you get them to me today or tomorrow, you get 1 bonus point. That's all the bonus points that are left, 1 for today or tomorrow. However, if you turn it in to me Monday, you just get your score. No bonus points, just your score. If you get it to me Tuesday or later, you start losing points. So, yes. Say that one more time. Okay, I'm not there. I was there yesterday because we had a meeting, but I'm not there generally. I'm usually there on Fridays, but we don't have Fridays in June and July, so I won't be there this Friday because school's closed this Friday. So what you need to do is get it to me on this campus. You know where my office is here? Okay, let me show you. If you go out, you can sit right there. I'll show you on my house. If you go out this door right here, here's where we are, and then take an immediate left, and then you'll see a half flight of stairs going down. Okay, go down those stairs, go almost to the end of the hall. The very end of the hall on the left is the stairwell. Just before that stairwell is an office. 265, that's my office. It's right next to a mechanical room like the one right here. Between the mechanical room and the stairwell, that's my office. If I happen not to be in, slide down the door. Okay? That's any work, not just this. So, sorry that I'm not on Birmingham campus, but if I was to drive to Birmingham campus, that's a half-hour driving. I wouldn't be able to grade papers, and I'm so far behind in grading papers. Which leads me to sort of my next little topic. That's how many I've got to go to grade yet not before I sleep, but before too much goes in the term. Yeah, I think I got everybody who just came in. All right. Because we had a big meeting yesterday for our department, the big meeting. It's a culmination of the year's planning and activities that met those planning, and they have this every summer right at the end of the term, which is a very inconvenient time. But anyway, we had ours yesterday, and because of all the data I had to collect and getting other people to submit their data, from last Tuesday, not yesterday, but Tuesday a week ago, until tomorrow afternoon at 3:30, I've gotten basically almost no papers graded because from Tuesday afternoon of last week, all day Wednesday I was in, class like today from 8 in the morning till 9 at night with 2 20-minute breaks and 2 10-minute breaks. That's all, okay? So in that time, I got nothing done. All day Thursday, when I wasn't advising or registering students, I was working on getting that report together. I did that all Thursday. I took it home with me over the weekend. I worked on it when I could over the weekend. And then finally, I got it sent Sunday evening. And And then Monday, of course, I was in class all day long. Had no time to do any grading. And then yesterday in the morning, I was spent doing the report. In fact, I had to cancel my yesterday morning class, the differential equations, because I had to go over to the Birmingham campus. That's where the meeting was, but I had to get documentation that one instructor had not gotten me until yesterday. And in fact, he was late getting it yesterday. So I couldn't do any grading yesterday. Actually, while I was waiting, I got a little bit of grading done, but not very much. And then, yesterday afternoon, I got a little bit of grading done, but not much, because I was getting all the labs and the tests and everything for these classes done, so we could, if necessary, we'd have them today. Especially the second class, I got a lot to give them. So, and then tomorrow morning, I normally have office hours from 10 to 12. I've got to extend my class tomorrow because I missed the class on Tuesday. So we're going to have an extended class tomorrow. That's why I won't be able to get it to any grading until tomorrow afternoon. So sorry about that. And Blackboard is even further behind. So I will get caught up, hopefully, knock on wood, this weekend. All right. Any questions on anything that we have done so far? Oh, I wish more people were here. I found out from one of my last classes that they have open student course evaluations. Okay, have any of you seen those yet? Have you done them yet? Okay. Do any of you non-Lawson students know how to do student course evaluations? No? Okay. Have you checked your emails? Is that how you know? Okay. If you'll check your Lawson State email, you will see the email. I haven't seen it because I'm not a student, and it'll have a link. And that link will then take you right to where you need to go. And please, please, please do the student course evaluation. We use them, and use them I use them to improve my teaching. I use them to evaluate my other instructors because I'm a department chair. They are well used, so please put forth the effort to do them. Now, periodically, I think every time, I don't know about summer. Sometimes they do them in summer, sometimes they don't. This summer they're doing them. Usually when you looked at yours, did you have any additional ones to do, or just the courses? Sometimes they're asked for library services, registration services, food services, maintenance, groundskeeping. I don't know. If you have any additional ones, please do those as well. Okay? Good deal. Any questions? All right. Topic 10 is thermal physics. This is probably the last chapter we're going to be able to do. If we have some spare time, we'll do a little bit in 11, which just builds on 10, but we'll see if we can get that far. What do we mean by thermal physics? Thermal physics is the study of temperature and heat, and how both of these affect matter. Now, if I said temperature and heat, what would you think? Are they synonymous, meaning the same thing? Are they related, or completely different things? Say again? Same thing? Is that what you said, or related? Huh? They're not quite the same thing. They are related to each other, but they're not the same thing. Temperature is a measure of how warm or cool something is. Heat is actually the transfer of energy. So actually temperature is measured in degrees or Kelvin or something like that. heat is measured in calories or joules, ETUs, or things like that. So they're not the same quantities, however they are related. And how these affect matter, that's what thermal physics is talking about. And by the way, this is first chapter in thermodynamics, which was the last thing that we were to cover in this term. Thermal physics, the descriptions require definitions of temperature, so we'll hit definition of temperature later, definition of heat, and definition of internal energy. Now, heat and internal energy are even more closely related, as you'll see. Heat leads to changes in internal energy, like I just said, and therefore to changes in temperature. So they are related, but these two a bit more directly, and then as a result, that affects the third. Gases are critical in harnessing internal energy to do work. That's an interesting statement. I basically never thought about that until I think, oh yeah, well that's true. Air conditioning, based on gases, okay, are critical in harnessing internal energy and getting it to do work. Did any of you drive here today? Guess what? It was the explosion in your cylinder that made very hot gases. That did the work that turned your wheels that drove you here today. So yes, I would say that's a pretty big contributor. Any of you use any electricity today? Sure. What you did, all electricity except hydroelectric electricity, that doesn't really use gases, but any electricity from a coal-fired power plant, natural gas-fired power plant, nuclear power plant, all those plants, the heat that you trap there is used to boil water, get it into steam, use that steam, high amount of energy to turn turbines, steam turbines, and that's what create the electricity, okay? So yes, gases are critical in harnessing the internal energy to do work. So some definitions here. I said that's the first thing we're going to do. The process by which energy is exchanged between objects because of the temperature difference is called the heat, okay? So here are several important keys here. Process in which energy is exchanged. Heat is not energy itself. We talk about heat energy, thermal physics, thermal energy. Really, heat is the exchange of energy. So energy is involved. We measure it in energy units, but heat is the exchange of energy between objects. So you have to have at least two different objects in order for heat to be passed, okay? Does it always pass? No. You have to have a temperature difference. Just like you have to have a height difference for kinetic energy or potential energy to happen, you have to have a potential difference for electrical energy to happen. You have to have potential differences. Here we have temperature differences. That's what creates the flow of energy, that exchange of energy, that change of energy is called heat. Objects are in thermal contact if energy can be exchanged between them. Okay, I'm not in very good thermal contact with that table over there, okay? I almost have to be touching the table in order to be in thermal contact with it. Now, if that table was a big ice cube, or there was a big ice cube sitting on the table, it doesn't really affect me until I get close enough to it and basically touch it. Now, if I get really close, I may feel a little bit of the heat being transferred from my body to the ice cube, but really the most of it is going to be by contact. So, objects in thermal contact if energy can be exchanged between them. Thermal equilibrium exists when two objects are in thermal contact with each other and there is no net exchange of energy between them. So let's say that this desk is at the same temperature as the back of this desk. If I bring them in contact with each other, there's not really going to be a lot of thermal energy because they're in thermal equilibrium. There were two objects that are in thermal contact with each other, and there's no heat exchange, net exchange of energy between them. Now, if I had taken this one out and heated it up with a blowtorch and brought it in and then touched it to the desk, then it's going to transfer heat to the other desk until they reach thermal equilibrium. So that's what you have to have, thermal equilibrium. They have to be touching in thermal contact with each other and not exchanging any heat energy between themselves. Now, sure, there could be some molecules bumping into this one, some into that one, but the net's going to be either zero or negligible. Okay? Now, I think it's largely attributed to a very smart, sort of unique kind of a scientist. His name was William Thomson. But he didn't go by William or Bill or Willie or Billy or anything else like this, because he was very rare, but he was very high aristocracy in England. A lot of times the really high aristocrats were not necessarily all that smart. They just were landowners, okay? They had the big fortunes. They had gotten it over time. Now, maybe their ancestors had been fairly smart. Who knows? They may have just done the king a favor and gotten a bunch of land. They may have been crooks and gotten a bunch of, whatever. But generally, they were landed gentry and didn't have to do much except run their estates. William Thomson was the exception. Quite an exception. He was a brilliant scientist. But they don't usually call him William Thomson. They called him Lord Kelvin. That was his title. Okay? And in my mind, or my memory, he was largely responsible for naming the 3 laws of thermodynamics. First law, second law, third law. We're going to probably hit all 3 this chapter. Okay? But long after he did those, someone, I don't know who, sat back and said, you know, we really need another law because all these are based on this assumption that really should be a law. And they didn't want to call it the 4th law of thermodynamics. Everybody knew the first 3 because it was foundational to the first one and the second and the third. So rather than name it the 4th, and they couldn't want to change all the numbers, they made it the 0th law. Okay? So that's why we have a 0th law. It's not that it's a nothing law. It's just, it should have come before the first, but William Thomson, Lord Kelvin, just assumed that everybody would know that was true, but really it should have been listed as a law. And here's what it is. If objects A and B, here are A and B, actually here are A and B, are, start over. If objects A and B are separately in thermal equilibrium with a third object, for instance, object A is in thermal equilibrium with this thermometer or whatever device that is to measure temperature, and object B is also in thermal contact with such an object, and they are at the same temperature, so they're in thermal equilibrium with the third object, then they have to be in thermal equilibrium with each other. Basically, and this is the law of temperature, by the way, if the temperatures of A and B are measured to be the same by placing them in thermal contact with a thermometer, which is object C, and they are shown to be in thermal contact with each other, thermal equilibrium with each other, then they would be in thermal equilibrium with each other if they were put in contact. Because if they're at the same temperature, there's not going to be an exchange. Okay? Then A and B are in thermal equilibrium with each other, even though they may not be touching. Okay? Object C could be the thermometer, or it could not. It could be something else. This allows a definition of temperature, and all the other 3 laws assume that we have a definition of temperature. This is what gives us a definition of temperature. And it goes beyond this. Here's an example. Someone describe a thermometer to me. Anybody? Describe a thermometer. It's what? tell temperature, but describe it to me. How does it tell temperature? Okay, you're describing the mercury thermometer. Okay? And you would say in it. What is it in? Glass, okay. And what kind is that? Is that one you put under your tongue? Is that one that you have hanging on the wall? What kind of thermometer are we talking about? Second.
The one you put under
Under
your tongue.
your tongue, okay. Now, here's the deal, okay. You put the thermometer under your tongue, and you have to wait a while. What are you waiting for? Yes, the heat to exchange, the energy to exchange from your body to the glass, because the glass is what's touching your tissue under the tongue, right? You keep your mouth closed and tighten things so you don't get cold air in there. That comes in thermal contact with your body. The glass does. But then the glass transmits that energy to the mercury, and then the mercury expands. You don't put mercury under your tongue. Please don't put mercury under your tongue, because it's a carcinogenic material. It's a heavy metal that can cause some pretty serious problems. Let me, talking of serious problems, here is, oh, no, I didn't mean it that way. Allison's here, okay. Okay. So you see, just the act of taking your temperature is an illustration of the zeroth law of thermodynamics. Your body gets in thermal equilibrium with the glass gets in thermal equilibrium with the mercury expands, rises, you read a thing, it's in thermal equilibrium with your body, and it's never touched your body. Okay? That's the allows a definition or even a measurement of temperature. The reason I said there are many thermometers out there. The thermometer in that box right there that's measuring room temperature, it's probably, it could be electronic, it could be electrical, it could be a resistance thermometer, it could be what they call a bimetallic strip in a coil. It could be any kind of thermometer. Okay, so whichever kind you have, it depends on the zeroth law of thermodynamics. Okay. So how do we get temperature from this zeroth law? Temperature is a property that determines whether or not an object is in thermal contact or thermal equilibrium with other objects. Two objects in thermal equilibrium with each other are at the same temperature, period. Two objects in thermal equilibrium with each other are at the same temperature. In other words, they've exchanged heat until they're in thermal equilibrium. No net energy is being transferred any longer. Then they're at the same temperature. So, what are thermometers? They're used to measure the temperature of an object or a system. Okay? By the way, I just noticed all X chromosomes today. Where are the Y's, huh? Okay, never mind. Used to measure the temperature of an object or a system. Your body would be a system. The object might be the desk or that cube of ice that's on the table. Or the system could be the room. Okay, the air from the room is entering there and exchanging. So that's the temperature of the object or the system. It makes use of the physical properties that change with temperature. Okay? There is no magic bullet that when an object touches something automatically it can measure the temperature. No, what you described in your thermometer was the expansion of mercury. Mercury expands when it's heated, contracts when it's cooled. So what you're measuring is a contraction or expansion of mercury. That correlates to the temperature, okay? And if you have the same temperature, it's going to expand the same amount. Other things like the bimetallic strip that might be in a thermostat, that is the difference of two metals fixed with each other, and when they heat or cool, they expand at different rates, and therefore you get the movement. In fact, a lot of the thermometers that you have that have the little arrow on it that points toward the temperature, like hanging on a tree outside or on a wall or something like that, that's a bimetallic strip, and as it heats, It moves up this, it cools, it comes back down. So that's a change of temperature between two dissimilar metals. In your automobiles, you have a thermostat, which is well, there could be several ways of this. One of those is a thermistor, which measures the resistance. The electrical resistance of an object depends on its temperature. So you're actually measuring electrical resistance, but correlating that to temperature. So it makes use of physical properties, whatever they are. Expansion properties, resistive properties, evaporation of water. I mean, there just could be tons of different physical properties that correlate or change with the temperature. Many physical, here they are. Volume of a liquid, we just talked about. Length of a solid, that's in the bimetallic strip. Pressure of a gas, held at a constant volume. So what you're measuring, trying to measure is temperature. What you're really measuring is pressure. And as the pressure goes up, you know the temperature had to go up. Pressure goes down, that meant the temperature dropped. Volume of a gas held at constant pressure. Okay? That would be, if it's a constant pressure, the bigger the volume gets, obviously has a greater temperature, the smaller at a lesser temperature. Electrical resistance of a conductor, I mentioned that in a thermistor. Actually, the color of a very hot object is a way to measure temperature to some extent. For instance, when we look at the spectral lines of a star out there, the astronomers do, they know that by the different colors of the spectral lines, approximately what the temperatures are on the surface of that star. The blue stars are always way hotter than the white stars. The white stars are way hotter than the orange stars. The orange stars are way hotter than the red stars. Yellow is in between there. Our sun is a yellow star. Okay? So the color of a very hot object could be a measure you use to measure temperatures. Okay. A mercury thermometer, like the one you described, is an example of a common thermometer. The level of the mercury rises due to the thermal expansion of the liquid. So here you have ice water, that is cubes of ice in the water, and this mercury thermometer, because the ice water is in thermal equilibrium with the glass is in thermal equilibrium with the mercury either shrinks or expands, probably in this case it shrinks down to around, whoa. That's not water, folks. I don't know what it is, but it's much colder than water. Ice water would be at 0 degrees Celsius. This is much colder than that. I don't know how much, but colder than that. That must be, say, liquid, I don't know. A liquid salt water. Yeah, that could be it. Maybe you've added a whole bunch of salts to this, and you have ice in that, and it's cooling down to something well below the temperature of water, ice water. Or you can heat that water, and now it's no longer no ice in it anymore, but you see steam coming off of it. Okay, now here's the problem, Houston. If that's 100 degrees Celsius, this is not water there either, because water boils at 100 degrees Celsius. If it's over 100 degrees Celsius, it's no longer water. It is steam. Now, if it was in a pressurized container, yes, by pressurizing the water, you can raise that temperature of boiling point. What did Mama or Grandma use maybe that did that? Use that characteristic. Maybe you've used one. Pressure cooker. Pressure cooker will cook foods much faster because of the pressure. You can get the temperature of the water to increase, and it cooks a lot faster. Okay? So this is obviously not under pressure because it's open. I can't think of any way, unless the whole room is pressurized a great deal, that then that temperature would be greater than 100 degrees. So let's say that's some other liquid, such as oil. Because oil will heat to a much higher temperature before it vaporizes than water. What's the activity you've used that shows that? Frying foods doesn't take nearly as long as boiling, does it? You fry an oil, the oil will go to a larger temperature before it evaporates. Water will go only to about 100 degrees Celsius. So you use that, okay? The level of the mercury rises due to thermal expansion. The temperature can be defined by the height of the mercury column. And that's why we have it graduated this way, so you can tell what the temperature is. It has to be calibrated by the factory to let you know exactly what you're doing. Now, cheap thermometers, they will maybe calibrate the first one and try to build all the others just like it. There's no guarantee there are just like it. There may be little variations in the glass or the size of the capillary tube or something else, and they could be off. So cheap thermometers, they'll be pretty close, but not guaranteed to be right on. Really expensive thermometers are probably individually calibrated to make sure they are reading the exact temperature. And speaking of exact temperatures, here comes essence. Okay. There you are. All right. But you're not really measuring temperature, you're measuring the height of a mercury column, which depends on the expansion rate of mercury, which is a surrogate measure for temperature. But it's a very good one. Now, thermometers can be calibrated, as I was just saying, by placing them in thermal contact with an environment that remains at a constant temperature. Okay? And here's examples of this. The environment could be a mixture of water and ice and water at thermal equilibrium with each other. And if they are in thermal equilibrium with each other, you're guaranteed they're at one and only one temperature. What is that? If ice and water are in thermal equilibrium with each other, what is that temperature? One of two names. It's either the freezing point of water or the melting point of ice. It's exactly the same temperature, and that is what? 0 degrees Celsius or 32 Fahrenheit. Okay? Another commonly used fixed temperature is that of water and steam. For water and steam to be in thermal equilibrium with each other, they've got to be at a particular temperature. And what is that one called? See, the boiling point of water or the condensation point of steam, for them to be in thermal equilibrium with each other. Okay? And that is where? Grade do y'all want on your papers? 100 what? Degrees Celsius, or, you probably wouldn't mind having this on paper, but you're not going to get it, 212 degrees Fahrenheit. That is pretty hot. Okay? So we will use those two as our calibration points. Okay? Now you could use other liquids, solids, gases, but you'd have to know what their boiling points, melting points, freezing points, condensation points are. And if you know that, you could use them as well. Water is the one that's closest to our normal conditions. Okay. Now, let me give you a little background here. May come as no surprise to you that the first person to come up with some type of really a working thermometer was good old Galileo. I mean, he started a lot of things going, scientific method, breaking out from the stranglehold that Aristotle had us in on why things operate the way they do, the whole thing of forces and uniform motion, all that stuff. Galileo started the ball rolling. Newton picked it up and took it further. Galileo started. And he started thermometry, basically. What he discovered or saw or realized that if he had a flask, and you've probably seen some of these, the flask that's sort of a bulbous on the base, a long, thin neck, okay, and then the other. Well, he basically put a fair amount of water in that flask, got it somewhere up into the neck, and flipped it over into a pan of water, okay, leaving air in the top of, now the bulb is now at the top, and air is in there, and when the air heats up, it's in thermal equilibrium with the glass. The glass is in thermal equilibrium with the room. So when the room heats up, it heats the gas and pushes the water down. Water is allowed to go up in the pan. Okay? So he then had his scales going low temperatures at the top, which is near the bulb, and then breaking it down as you went down. Can anyone think of any possible reason that wasn't the most accurate of thermometers? Water was exposed to the atmosphere, right? Well, if a high pressure system came through, the pressure of the Earth's atmosphere pushed down on the water, forcing water back up without a change in temperature. If a low pressure system came through, and then the water came down because the air was lower pressure, so you were actually measuring barometric pressure in addition to temperature, and it was hard to separate the two. Well, who followed Galileo? Isaac Newton. Isaac Newton had read and studied about Galileo's thermometry experiments and what the problems were. And by the way, they never met. Newton was born on Christmas Day, the same year that Galileo had died. So they would never have met, and even if they had met, it would have been an old man and a baby. So, they wouldn't have changed much. But Newton read extensively of Galileo's work, and he came up with a slightly better system. He filled a capillary tube full of mercury, I assume it was mercury, and sealed it off, and then flipped it over, and the mercury went down into a reservoir, but there was no air involved, no opening to air. So now all you were doing is measuring the temperature of the mercury, thermal equilibrium with the glass, which is thermal equilibrium with the room or the body or whatever it was measuring, and then the mercury went up and down. That's the scale we use. Well, Newton, for want of anything else, just said, let's have the scale being from the freezing point of water, let's make that a 0, to body temperature. Why not? So body temperature, and let's make that 10. Okay? So 0 to 10, freezing point of water to body temperature. Anyone see any possible problems with that? We all don't have normal temperatures of 98.6. That's kind of an average value. I worked with an engineer when I worked for Southern Research Institute. She was our coordinator of work down in Florida, and she would send me data, and I would process, analyze, the data, and I'd order things for her. So we worked together fairly closely. But one time when I was down there, she said something. She said, I can't remember how it came up, but she said, "Oh no, if I have a temperature of 98.6, I have a pretty high fever." She said her normal body temperature was closer to 96. I don't know why, it's just her metabolism or something, her normal body temperature was not 98.6. So therefore, you'd have sort of a hard time calibrating the system if different people had different body temperatures, which we do. And who knows, that person may have a fever one day, on the day he or she was trying to calibrate. And we got our first Y chromosome. Drum roll, please. Okay. Ryan is here. Okay. So, that is what Isaac Newton contributed. Got a much better thermometer, but in order to calibrate it, he probably didn't choose the best things. Freezing point of water, not bad. Body temperature, not the best. And that was a 0 to 10 scale. Well, a bit later, a German guy named Gabriel Fahrenheit was doing a lot of experiments at very cold temperatures in his lab. Now, how did he get the cold temperatures? Well, he would get ice water with lots of ice in it and put salt on it. What does salt do to ice water? Second? Make it colder. Drops the freezing point. So he was able to get his lab to get down to temperatures that were, say, minus 30 or so. Minus 3 or so on Newton's scale. And he didn't like having negative numbers. He wanted to deal only with positive numbers. So he turned around and said, I want my 0 to be as cold as I can go in my lab, which is so much salt and so much ice, and how cold will that make the water go? So that's where he set his 0, which moved up the scale where the normal melting and freezing point of water and ice is, and now it's at around 32 degrees on this Fahrenheit scale. Well, when they did adjustments to it and refined it a little bit, they found out normal body temperature wasn't at 10. Well, let me back off from that. I'm sorry, a little above 3 on Newton's scale. And then that made body temperature somewhere around 10. Okay? And the coldest Gabriel Fahrenheit could go in his lab, around 0. Okay? Well, what's wrong with that picture? Other people may get colder temperatures in the future, and we sure did. So the Fahrenheit scale is not very good. It still is based on now a slippery slope on one end, salted water, and a slippery slope on the other end, variable body temperatures. Okay? So, and here's another issue that came up. If we were going 0 to 10 on that, that's covering a wide range of temperatures. Huge range of temperatures. So people started talking first in half degrees, then in quarter degrees, and ultimately in eighths of a degree. Okay? Now, after a while, since they were using eighths and using them very consistently, they quit calling them eighths. They just said what that number was and called that the degree. Darius is here. So that's when we came up with degrees. Now, rather than going from 0 to 10, we were going from, did I say it right? Yeah, I think so. Good deal, thank you. Good deal, thank you. There's another paper in, good deal. And several more tests and stuff too. Anyway, we came out with, rather than, I think I said that wrong. Newton went up to 12, okay? And 12 eighths, 12 times 8 is 96. So that became the body temperature. Rather than talk about eighths of a degree, they just started those eighths of a degree degrees, and 12 times 8 is 96. Okay? So that was the body temperature. Well, when they did adjustment for it and stuff like this, it got it up to 98.6. So that's how we got such a weird temperature for body temperature. They were shooting for 12 and then did by eighths. That made it 96, and then by adjustment and calibration got it up to 98.6. And that made the freezing point around 32. And others looked at that and said, this is kind of crazy. Why? Gabriel Fahrenheit's lab temperature, we can get colder than that. Why have body temperature be the upper end, even though it's not exactly on the money anymore? We can do better than that. Let's go back to the idea of freezing point of water and boiling point of water. And that's what Anders Celsius, I think he was Swedish, I'm not sure, I believe that's right, scientist, he said, let's do the ice-water mixture at 0 degrees. Now his original scale, he called it the centigrade scale. What does centi mean? 100. So he put 0 as his 0 degrees Celsius as his ice-water mix, the ice point or the freezing point of water, also the melting point of ice, you can call it that. And the temperature of the water-steam mixture was then 100 degrees Celsius, okay? A 100-point scale. That's the steam point or the boiling point, technically the condensation point of water-steam system, okay? The distance between these 2 points is divided into 100 equal seconds, 100 degrees Celsius. Now, all right, Nick is here, and Will is here. There's Nick, and there's Will. All right. Anyone else come in since I called off? All right, we're on, time out. Quick quiz, 10.1. 2 objects of different sizes, different masses, and different temperatures are placed in thermal contact with each other. Okay? Choose the best answer. Energy travels A, from the larger object to the smaller object. B, from the object with more mass to the object with less mass. C, from the object at higher temperature to the object at lower temperature. Where does energy travel? A, B, or C? A was from larger object to smaller object. B is from object with more mass than the object with less mass. And C is from the object at higher temperatures to the object at lower temperature. A, B, or C? Call out something, somebody. Anybody? C, for sure. Okay? I'll even check in the back of the book that that's not really necessary. I think we all could probably agree on that. This is, but let me put my paper in the right place anyway. 10.1 is C. Good for them. Okay. All right. Went right past that. Okay. So there's this. Okay. Originally, he called it the centigrade scale, and later they named the scale after him and called it the Celsius scale, and that made it a capital C. Because centigrade wouldn't necessarily have been capitalized. I don't know what they used, but it didn't last very long because they named it after him, probably after his death, and they named it the Celsius scale, so that's a capital C. What's the other scale that I mentioned?
Fahrenheit.
Fahrenheit, named after Gabriel Fahrenheit. So therefore it has a symbol of
F.
capital F, okay? Now, Both of those scales do use the degree symbol. The other scales we'll talk about do not. Okay, only one other scale. Okay. Okay. Now, trying to see if the new edition has this gas thermometer. I don't see it in here, so I may just skip on past this. I sure don't see it. Oh no, there it is. Okay, it's in 10.2.1. Very page I was looking at. I just looked at the next page. Okay. Temperature readings are nearly independent of the gas. Okay? Just about all gases expand when they heat, contract when they cool. Expand when they heat, contract when they cool. Okay? And the temperature readings are generally independent of the gas. As long as the gas pressure is low. Now, if you start having pressurized gases at fairly high pressures, now the temperature relationship is not quite as easy and simple as it was before. Temperature needs to be well above the temperature at which the gas liquefies. Okay? We don't want gases condensing on us, because then you have a lot of latent heat involved, and that messes up everything. Pressure varies with temperature when maintaining a constant volume. Okay? We mentioned that before, and that, by the way, is pressure varies with temperature. I think that's Boyle's law. Okay? Pressure varies with temperature when maintaining at a constant volume. Okay, the volume of gas in the flask, this is the gas in the flask. Gas in the flask, sounds like a Dr. Seuss story, doesn't it? Is kept constant by raising or lowering the reservoir of mercury to keep the mercury level right here. And column A constant. So they're calling this column A, this column B. Okay? So they're trying to keep the volume of gas in this, the volume equal, because the volume of gas is in all of this here. And how you do this is raising or lowering this thing to make sure that it matches here, and that tells you that you're at constant volume. And I was trying to think what the term for that is. Constant temperature would be isotherm, isothermal. Constant volume, I think, is I know at constant pressure would be isobars. Okay, same pressure. Just can't remember what it is for. I've heard it called isotonic, but I don't think that's maybe. Okay. But anyway, what you do is let this go up and down to keep this volume exactly the same. Okay, right at zero here. Wherever that is, keeping this at zero by raising this up and down, that keeps this one right here, keeping this volume the same, even though its temperature may change greatly. Okay? That's the bath or the environment to be measured. That's a flexible hose that lets you go up and down the mercury reservoir. You let that P0 go up and down, the H varies greatly. but the, yeah. I think that's all we can say about that now. Now, let's look at this graph. I think I may have mentioned it before, but if I haven't, I'll do it now. All gases, all gases respond, and they heat, they expand, and they cool, they contract. And if you were to plot different gases, because they're different materials, this gas at 100 degrees Celsius would be at this volume, whatever that, this pressure. 100 degrees Celsius would measure a pressure here. Drop it down to 0 degrees Celsius, it would be a pressure down here. Do the same here, this gas, and you get these things. Well, if you extrapolate this data, these data, and maybe even get some lower readings, some higher readings, in here, you see they do follow almost a straight line path. And the unusual part, they all seem to coalesce at the same point. Now, where is that point? 200 minus 273 degrees Celsius. Okay? Now, here's a couple of things. Actually, negative 273.15 Celsius to be more precise. Okay. Even though you may have some more data points here, and many you won't do up there, why do they have a dotted line here? Why didn't they keep dropping the temperature and measuring the pressure of the gas? What was wrong with that suggestion? What happens when you drop the temperature of the gas? Every gas, any gas. What happens if you keep dropping the temperature of the gas? What happens if you keep dropping the temperature of the what? Okay, it does contract up to a point, but at some point, what happens to every gas? If you keep getting colder and colder and colder, what happens? It liquefies, exactly. Because it changes phase there. No longer just changing, and we talked about that in the last chapter, didn't we? Solids, liquids, and gases. Yes, you keep changing, taking energy away, dropping the temperature. At some point, it will liquefy, and then the volume goes to almost zero compared to what it was as a gas. So every one of these, at some point, is going to abruptly go down to zero. Okay, different gases that will be at different points. That's why you have to extrapolate, and getting several points is helpful. And when you do that, they all tend to fall from the same thing. You'll never get there. The gases can't get there. They will first liquefy, and then after they liquefy, they're going to solidify. And even then, you've got some more temperature you can get off. You can never, well, we'll get there later. Anyway, this point, that temperature at which that supposedly the pressure goes to zero, if you get it that cold, that is called absolute zero. Okay? Now, why absolute zero? Second?
It can't get colder.
You can't get colder, absolutely. What do the double bars like this in mathematics mean?
Absolute value.
Absolute value, which means?
It's always a positive.
Only positive, okay? And that's why really they wanted this scale anyway. Remember good old Fahrenheit? He didn't like having negative temperatures. It may have just been a preference with him. But guess what? When we get into some of the formulas and equations we'll get to later in this chapter, for instance, kinetic energy, the average kinetic energy of an object is related to its temperature. That's how we really now define temperature. Average kinetic energy of its molecules. Guess what kinetic energy cannot be? What's the point? It cannot be negative because it's 1/2 mv squared. 1/2 is positive, mass is positive. You can't have a negative mass, not that I know of. And when you, whatever your velocity is, you square it, it's got to be positive too. So how can you have a temperature that's negative if it's related to kinetic energy, which is always positive? So that's why we needed a scale for temperature, unlike Celsius, that easily can get in the negative range. I mean, in the wintertime here, we get below 32 Fahrenheit, which is below 0 Celsius. That's like when you're making, what activity do you use to put salt on ice?
My activity.
Yeah, what activity have you done in your life that you put salt on ice to drop that freezing point? Making ice cream, exactly. Because you see, if you just had ice around that container and churning it and churning it and churning it and churning it, you're never going to make ice cream. Why? Because what is milk mostly, or cream either? Mostly water. But it's water with dissolved things in it, like proteins, fats, and all sorts of other things, calcium particles and stuff like that. They're dissolved or suspended in the milk or cream. Well, guess what? If you have something dissolved or suspended in a liquid, you're dropping the freezing point. So no matter how much you churn the ice cream, you'll get butter before you'll get ice cream. Okay? No doubt about it. Okay? So what you have to do is put something on the ice to get it even colder than the water, so you can start making that water freeze in the ice cream. Okay? So that's why you put salt in water, just like Gabriel Fahrenheit did. Salt on the ice, so you drop the melting point and freezing point of that water and ice. Okay. But even then, you can get negative temperatures. Like I said, here in the wintertime, not super frequently, but quite often we'll get below freezing. And then your temperature is a negative temperature, negative Fahrenheit or negative Celsius. But on this scale, the absolute scale, you will never, ever get a negative number, because that's as cold as you can go. You can't get any colder than that. Okay? And what's even more, you can't get there either. Okay? You can get close to it, but you can't ever achieve it. We'll get to that later. That's why it's called absolute zero. It's always a positive number, an absolute value, and you can then do all your manipulations with it, and you come up with positive pressures, positive volumes, positive everything. You can't, kinetic energy, you can't have negatives if you're using that. Now, if you prefer the Celsius scale, and by the way, a Celsius degree is the same size as these degrees, absolute temperature. Everything's measured that same size. So we'll get to that in just a minute, but keep that in mind. Okay? Guess what we named that absolute scale? After good old William Thompson, who was Lord Kelvin. So that's where the name Kelvin scale came from. Now, when the pressure of a gas goes to zero, which it never really can, and it won't be a gas if it goes to zero, because it will not be a gas at negative 273.15 degrees Celsius, because it would have already liquefied long before that. That temperature is called absolute zero, not on the Celsius scale, on the Kelvin scale. That's the 0 point of the Kelvin scale. So, negative 273.15 degrees Celsius is equal to 0 Kelvin. Now, what do you notice the difference between Celsius and Kelvin scale? Celsius always uses the degree symbol. Kelvin never does. So never refer to so many degrees Kelvin. I will find myself saying that because I'm used to talking about temperatures in degrees. In the Kelvin scale, it's not. 0K, 15K, 273K, whatever. It's just some number K. Now, how do we convert from Celsius to absolute then? And by the way, the absolute scale, you could put T sub K, but they just call it T. Anytime you see a capital T in your physics, you generally assume that's going to be the Kelvin scale. If you're talking about temperature, that's the SI unit, okay? And so degrees Celsius is whatever that Kelvin temperature is minus that 273.15. The size of those degrees are the same, it's just how they're marked are different. One is you might say a vertical shift from the other, okay? The size of each degree is the same. That's a Celsius. Okay. Now, the modern definition of the Kelvin scale defined in terms of 2 points. These were agreed upon by the International Committee on Weights and Measures, and in 1954, 3 years after I was born, okay, I'll have to get some water, I think. The first point in that scale is absolute zero. It's rather bizarre they use absolute zero because you can never get there, okay? But you can get awfully close. The second point is the triple point of water. What in the world do we mean by that? There is one and only one place where water can exist in liquid form, solid form, and gas form at thermal equilibrium. That's the triple point of water. Okay, and that is a pretty cold temperature, I think. The triple point is the single point where water can exist as a solid, liquid, and gas in equilibrium with all the others. Why don't they give us that number here? Single temperature and pressure, and you have to specify that. It has to be what they say is standard. On our single temperature, of course, that's the temperature you're looking for. So I would say a fixed pressure and volume. Now this occurs at 0.01 degrees Celsius. Why did they just say zero? Okay, that's awfully close to 0 degrees Celsius. Okay, but not at normal pressures. It's at a pressure of 4.58 millimeters of mercury, which is very, very low. What's normal pressure in millimeters of mercury? Anyone know? Okay. Typically it's called 1 atmosphere of pressure, and that almost certainly is 760 millimeters of mercury. Okay, so this is a extraordinarily low pressure and right near the freezing point of water. And at that point, the solid, liquid, and gaseous water will all occur at the same temperature and pressure if you're at 4.54 millimeters of mercury. Okay. Trying to make sure I haven't skipped anything else. All right. Modern definition of Kelvin scale continue. The temperature of the triple point of water, okay, we said what it was on the Celsius scale. What would that be on the Kelvin scale? It's 0.01 degrees Celsius. What would that be on the Kelvin scale? Anybody? Help me. What would 0.01 degrees Celsius be on the Kelvin scale? What is 0 on the Kelvin scale? 273.15 K. what would 0.01 degrees Celsius be on the Kelvin scale? Add 0.01 to 2.73. What do you get? That's it. I think I said the wrong number. 273.15 plus 0.01 is 273.16 K, not degrees K, K. Therefore, the current definition of the Kelvin is defined as 273.16 of the temperature at the triple point of water. Okay? Now, thinking about introducing something else, but I think we'll wait. All right, let's look at some Kelvin temperatures, some representative Kelvin temperatures. Okay? Now this scale is logarithmic, okay? Because you're going from very, very, very cold temperatures to incredibly high temperatures. Okay? Now this is the part, they say here absolute zero has never been reached. So we'll get to this a little bit later too. I keep promising that, but we'll get to it. Now, this is the part that sort of blows my mind. How close to 0K have we gotten? 10 to the minus 10 K. That's 0.0000000000001 K. What kind of device do we have that can measure to the nearest 100 billionth of a K? I didn't know there was anything. So how do you know we're not already at absolute zero? You can't convince me. That is, like I said, 10 to the minus 10K is 10 billionth of a K. Unbelievable. Liquid helium. And this is sort of surprising. Liquid helium is actually colder than liquid hydrogen. I would have thought liquid hydrogen would be colder, but it's not. Liquid helium is something about 12K. Liquid hydrogen may be liquid helium would be about 0.1. About 0.12K, okay? I believe. No, 1.2K, 1.2K. We barely can get there, okay? So how in the world can we get 10 to the minus 10K? Liquid hydrogen is about 11K, okay? Liquid nitrogen is, this is a log scale, so they don't run evenly here, but I would say that's fairly close to, I think it's in the 30s and 40s. Okay, water freezes at what? Water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, which would be
100K.
How much?
Is that 100K?
What's the difference in Celsius and Kelvin?
Oh, it's salt water.
273.15 Celsius is 0 K. So therefore, 0 Celsius, add 273.15 there, you get 273.15 there. So that would be 273.15. So this is 100, 200 would be somewhere there, and that would be 273, water freezes. Copper melts at around 1,000 K. Surface of the sun, that looks to me to be about 4,000 K. The solar corona, these are coming from the back of the on the surface of the sun, when you have these flares that are going up at really high temperatures, that's what they mean by this, and that would be right around 6 million, 1 million K. 10 to the 6 is 1 million K. Interior of the sun is about 1 billion K. No, 10 million K. 10 million K. A hydrogen bomb, which I find sort of suspicious here because the interior of the sun, I would think that's a hydrogen to helium fusion reaction. Same thing as you have here. Why is this an order of magnitude hotter? I just don't see that. Okay, that would be about 100 million K. Okay, really up there. Notice there is a minimum on this Kelvin scale, 0. You cannot get any colder than that. Is there a maximum? Not that we know of. I bet you some of those stars who are fusing helium into carbon, much higher than this. And those that are fusing carbon into iron, much higher than this, okay, as in a nova, a supernova, okay? So, yeah, it can keep climbing. As far as we know, there is no maximum temperature on any scale, even Kelvin. But there is a minimum temperature on every scale, and that's going to be where 0 Kelvin is. Now, again, they say absolute 0, meaning Kelvin, has never been reached. Even so, they say they've gotten to 1/10 billionth of a K, which to me is incredibly tiny. So anyway, I don't see how they can get that close and know they're not at 0. So let's look at the Fahrenheit scale. We mentioned it early on. It's the most common temperature scale used in the U.S. and in a few other countries in the world, but very few. Have any of you ever been to Canada? Do not use the Fahrenheit scale. Celsius. Mexico. Do not use the Fahrenheit scale. Celsius. Europe. Do not use the Fahrenheit scale. Celsius. Everywhere in the world that I know of, there may be a few small countries that do just about all the trading with the U.S. that may still use the Fahrenheit scale. Germany, where Fahrenheit came from, Celsius, they don't use the Fahrenheit scale. Now, I'm not saying that everybody in Great Britain doesn't, but officially, Britain uses the Celsius scale. I would be, well, I don't know, since Canada is Celsius, I bet you Britain is too. Temperature of the ice point, or freezing point, or melting point, whichever you want to call it, 32 degrees Fahrenheit. Temperature of the steam point, or boiling point, or condensation point, 212 degrees Fahrenheit. So what's the difference between these two temperatures of Fahrenheit? (180 degrees Fahrenheit). What is that difference between the ice point and the steam point and the Celsius scale? 100, because it's 0 to 100. So therefore, a Celsius degree is almost twice as big as a Fahrenheit degree. Not quite, 1.8 times. Okay? because there's more Fahrenheit degrees in between those 2 points, and they're the same points, okay, as it is in the Celsius scale. So we have a ratio, 180 to 100. What does that ratio reduce to? 180 to 100, or 100 to 180. Boy, this high-level math is tough, isn't it? All right, here's breathe. What's that ratio? 100 to 180, or 180 to 100? Come on, folks. Say again? I don't think so. 180 to 100. That's 18 to 1. Did you say 80 or 18? Huh? It's really 18 to 10, which is 1.8 to 1, right? Or, if you don't want to get decimals, that would be 9 to 5. And you thought it was a Dolly Parton song, didn't you? No, it isn't. Well, it is, but that's not the same thing. 9 to 5. Okay? Or 5 to 9 if you turn it over the other way. Hang on to that concept. It will be important. Okay? So here are those, let's go back here. Let's use that 9 to 5. This says 9 degrees Fahrenheit to every 5 degrees Celsius. So which way you want to go? Fahrenheit to Celsius or Celsius to Fahrenheit? Which are you measuring and which you want to go to? Name it. We're going to do them both. Pick one. Fahrenheit or Celsius? Doesn't matter. Pick one. Fahrenheit. Okay? So let's say we know the degrees Fahrenheit, whatever they are. What are we going to need to multiply by to get to degrees Celsius? Well, remember our rule? Multiply, get the units in their place. What unit will go where? You're trying to get this ultimately to be degrees Celsius. This is where the numbers go. This is where the units go. What unit goes where? One's on top, one's on bottom. Which one's on top, which one on bottom? It's not that hard, folks. Fahrenheit on bottom, so they'll cancel out, and degrees Celsius on top, so that'll be where it belongs. And what's that ratio? How many Fahrenheit degrees to Celsius degree, or Celsius degrees to Fahrenheit degrees? What's the ratio? Okay, well, actually, 5 degrees Celsius to 9 degrees Fahrenheit. You have to flip them over if you're going to flip the units. So get the units in their place and then match the numbers with the unit. So give me a degree Fahrenheit. I don't care what. Make up a number. 25. Pretty cold, isn't it? 25 degrees Fahrenheit. Okay? I'm going to multiply by that, but I can't do it yet. Because you see, 25 degrees Fahrenheit is negative Celsius. So I'm going to have to subtract something from this. And what you reckon I'm going to subtract? 32 degrees Fahrenheit, because that is the freezing point of water. That will correspond to 0 over here, so I have to first do that. So here's what we do. To get degrees Celsius, we take degrees Fahrenheit, subtract 32, and then from that multiply by 5 over 9. 5 degrees Celsius for every 9 degrees Fahrenheit. There's the formula for converting Fahrenheit to Celsius. Right there. Subtract 32, multiply by 9/5. That gives you degrees Celsius. And if you put the degrees on it, you know this is degrees Fahrenheit, you know this is degrees Fahrenheit, you know 9 degrees Fahrenheit plus 1 is 5 degrees Celsius, so that gives you, the Fahrenheit cancel out, and that gives you degrees Celsius, just like we expected. Okay? Now let's go the other way. What if you're given a degree Celsius? Name one. Name some degree Celsius. 45? Okay, 45 degrees Celsius. By the way, you're going to find that that's pretty warm. What are we going to have to multiply by? What unit goes where? Which on top? Which one? 9. Okay, well, put the units in the place first. You're right. You put degrees Fahrenheit on top and degrees Celsius on the bottom, so you can cancel degrees Celsius out. And this was 9 degrees Fahrenheit for every 5 degrees Celsius. Okay, 5 will go into 45 9 times. That's 81 degrees Fahrenheit. Not quite, though. That's 45 degrees Celsius is 45 degrees above the freezing point, right? So this 81 degrees Fahrenheit is 81 degrees above the freezing point. So you have to take that and add to that 32, because that is the freezing point. That gives you 103 degrees Fahrenheit. I hope we don't see any of that this year, okay? It's bad enough when we're 90 degrees here, and this humidity, 95 was yesterday, was pretty hot, okay? 103 Fahrenheit, that is a really, if you ever drive by a thermometer in Mexico that says 45, meaning degrees Celsius, you know it's hot outside. You're probably already aware of that. It's about 103 degrees Fahrenheit, okay? So what we did here, we took degrees. To get degrees Fahrenheit, we had to take degrees. Our ratio was 9 to 5, 9 degrees Fahrenheit to every 5 degrees Celsius, times your degrees Celsius, but then add the 32 degrees Fahrenheit. Okay? So notice on Fahrenheit to Celsius, you subtract first, then multiply by your divisor. This one, you multiply first, then add your 32. So you get there, and here you see, that's what shows up here too. Degrees Fahrenheit is 9/5 times degrees Celsius plus 32. Multiply first, then add. Here we subtract first, and then multiply by the percent. Okay? Now, to go back to Kelvin, if you have the Kelvin temperature, subtract 273.15 from it, you've got degrees Celsius. Degrees Celsius. If you had degrees Celsius, add 273.15 to it, and you have K. Not degrees K, K. And then these two are based on the fact that the change of temperature of Fahrenheit to the change of temperature of Celsius, 5 degrees Celsius corresponds to 10 degrees Fahrenheit, so you have to multiply those 9 to 5 ratio. Going the other way from degrees Fahrenheit to degrees Celsius, multiply by 5 ninths. In other words, multiply those sides by 5, divide by 9. Okay, good deal. Any questions on that? Here is sort of pictorial of what we're talking about. This is the ice point of water. That's what we call ice point. There's the steam point of water. That's why we call it steam point. Okay? And that would be 100 degrees. So it was like 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 down. So that would be 10, 20, 30, 40, 50, 60, about 72 degrees Celsius. Guaranteed that is hot. Very hot. Very, very hot. Okay? On the Fahrenheit scale, notice these Fahrenheit degrees are a little bit more than half of a Celsius degree. This is your ice point of 32 here, your steam point of 212 there. I don't even know how they do these. So it looks like that's 42. So it's 42, 52, 62, 72, 82, 92, 92, 12, 122, 132, 142, 152, 162, 172, 182, 202. I think they just blew in there. Okay, I may have messed up somewhere. On the Kelvin scale, and by the way, that temperature here, I don't quite have it thing, but let's say go back to 42, 52, 62, 72, 82, 92, 102, 112, 122, 132, 142, 152, around 162 degrees Fahrenheit. I don't want to see that. Okay, that would be what we would say that was 72 degrees Celsius. Okay, on the Kelvin scale, that's 273.15 K. Don't ever say degrees. K. And that would be 273. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So that would be 283, 293, 303, 313, 323, 333, 343, maybe 346, or something like that. Okay. Kelvin. Okay. Okay. Okay, that's 0 Kelvin. Never mind. Any questions? How you compare temperature scales? Now, example 10.1 is skin temperature, talking about that. And by the way, anyone been to the doctor recently? Very seldom. Okay, my doctor's office, they still put the thermometer under my tongue. Yes, but when I go to get a treatment, they just rub the thing across my skin. And they correlate the skin temperature to what you are. So this is a 10.1 is talking about skin temperatures. 10.2, extraterrestrial, not visitors or something, but temperature scale. And then we move to 10.3. I want to make sure I haven't skipped any. Nope, only one quick quiz so far. So now we're ready to move to thermal expansion of solids and liquids. This is 10.3. Gases certainly expand too, but their scale is a lot bigger, and a lot more things interfere with it, like pressure and things like that. Whereas pressure doesn't have too much to do with thermal expansion of water or solids. So let's look at thermal expansion of solids and liquids. The thermal expansion of an object is a consequence of the change in the average separation between its constituent atoms and molecules. So let's first think about solids. Solids are in this rigid crystal structure, remember? But those atoms and molecules vibrate. And if you increase the temperature, they vibrate faster. And if they vibrate faster, then the average distance between them expands a little bit. Not a lot, but a little. Liquids are the same thing. Here, the molecules stay in close proximity to each other, but when you heat them up, they're bouncing into each other, therefore have more kinetic energy, greater momentum, the collision, so they can spread farther apart. So in both of those, the thermal expansion of an object is a consequence of the change in the average separation between the constituent atoms and molecules. Heat them up, the average separation increases. Cool them down, the average separation decreases. At ordinary temperatures, molecules vibrate with a very small amplitude. As the temperature increases, the amplitude increases, that causes the object as a whole to expand. Ever so slightly, especially solids and liquids, don't expand that rapidly. But you can read it on a temperature scale, can't you? On that thermometer? Seems like it's going up pretty good, right? Notice the size of that tube. It's a capillary. It's extremely small. So a small change of volume down here in the bulb is going to make a big difference up here. That's why you can see it move, because it's moving a very small volume. Same thing we do with solids. That's why they take those bimetallic strips and round them into a coil. So that in reality they're really long, but they're wound into a coil. And then when the coil expands just a little bit, it's magnified, okay, because it's such a long strip. Okay, here is that formula that defines that for small changes in temperature. In other words, what's the change in temperature? Where do you see change in temperature in that equation? What would represent change in temperature? Delta T or T minus T0. Either one of those is a change in temperature. That is a delta T. Okay? Now, remember when I said most of the time the delta T stands for what? Or T, I'm sorry. T stands for what? Capital T? No, little t is time. Capital T is temperature, but what scale?
Celsius. Kelvin.
All right, good. Okay. Multiple choice here. Okay. So, Kelvin, most of the time. But guess what, folks? Does it matter here?
No.
Why not? Multiple choice again, right? Yeah.
Coefficient. No.
Yeah. Because a Kelvin degree, I said it, a Kelvin is the same size as a Celsius degree. So if you're doing a difference between 273 and 373 is 100. K, or 0 to 100 is 100 C. That's the same thing. That's the same difference. So delta T can be either Celsius or Kelvin. Now, if you're dealing with Fahrenheit, then you have completely different units here. But, with this. So here it is. The change of length, this is usually of a solid, is this coefficient of linear expansion. Alpha is the coefficient of linear expansion times the original length times your change of temperature. So this coefficient of linear expansion must be per degree. It could be per degree Kelvin, or per K, or per degree Celsius, usually. Okay? It says see table 10.1. And here is 10.1 on page 327. And notice this says per degree Celsius. Again, that would be equivalent number if you're doing per K. Okay? Aluminum, 24 millionths. Brass or bronze, 19th millionths. Okay? Remember that brass cube we used in lab last time? It may have been a bronze cube. They're very similar. Concrete, 12 millionths per degree Celsius. Copper, 17 millionths, pretty close to brass or bronze, because copper is a big ingredient in both of those. Ordinary glass, 9 millionths. Pyrex glass, 3.2 millionths. Invar, which is a nickel iron alloy, I would think they probably make magnets out of that, but I don't know for sure. That would be 0.9 millionths. Okay, lead, 29 millionths, back up there, bigger than aluminum, just a little bit. Steel, 11 millionths. Okay, those are your solids. Look at your liquids. But liquids don't have linear expansion. Theirs are volume expansions. Because liquids, there's no line of a liquid, okay? You can't really do that as a volume expansion on a liquid. Okay, and that's 1.5. Let me change that to 0.15 thousandths, 0.124 thousandths for benzene. Acetone was the first one. Ethyl alcohol, 0.112. Gasoline, 0.96 thousandths. Glycerin, 0.485 thousandths. Mercury, well, you can read the table. But look at air. Air is 3.37 thousandths, okay? Where everything else was point something is 3. Helium, almost the same as air, 3.665 thousandths. Okay. All right. Okay, before we get to that, there is a really neat, some people wouldn't consider it very neat, picture in your book, Thermal Expansion. Extreme heat of a July day in Asbury Park, New Jersey, caused these railroad tracks to buckle. That's one expensive mistake. What do you think they did wrong there? I don't know if you can, I think they're going to show this. No, they're not. If any of you have your book, you don't. Okay, only a few. Okay, this train track looks like this. Okay, that would be one miserable thing to try to navigate because not necessarily would do the separations stay even with each other. I think the train would probably derail if you tried to go over that track. What did they do wrong? Here's my guess. My guess, they laid these tracks sometime near the middle of winter. And when they did, they jammed those rails right against each other. Then when summer came and they had to expand, they had nowhere to go. So they went wherever they could. That was off the line. Have you ever listened to a train moving down the track? What does it sound like? Click, 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 click. What it is, the wheels, metal wheels, are hitting those expansion joints. And you've got to have those expansion joints, or else you get buckled. Now, bridges have to have expansion joints. They're mostly steel. You've got to have those expansion joints. That's why quite often you go over an overpass or a bridge, you'll get at each end. You've got to have some give there. Now, what they've started doing nowadays is putting these finger-type connections. Have you ever noticed that on the road? When they expand, they push together like this, and they don't produce as big a bump. When they contract, they go like this, and you just they'll have continuity without having as big a bump. Look at your road sometimes. The more modern bridges will mostly have those finger expansion joints. You've seen them? Have you put them in? Oh, okay. It sounded like you knew. Okay. What's that? Oh, okay. All right. And then the next is the bimetallic strips and thermostats. So I think we'd better hit applications of thermal expansion, the bimetallic strip. I'm trying to see this. Oh yeah, here it is. It's in this Applying Physics 10.1. Thank you. Applying Physics 10.1. That's where it is. Now, what they do here, in every thermostat is something that controls temperature. Let's see. Just see. Have we just moved from class period to lab period? She didn't quite make it to lab. Okay, close but no cigars. Well, we actually went straight through, so I'll give her credit for it. Let me go on and mark the roll for this before we hit bimetallic. FA still hasn't made it in. Nick is kind of here and leaving. Okay, no. Tiara hasn't made it in yet. Courtney Brooks is still here. Raven hasn't made it in yet. Give you a thing over here. Well, because I have to make up for Tuesday's class, my first one normally would be 8 to 9:50, but tomorrow I'm probably going at least 8 to 11 and maybe 8 to 12. Maybe not quite that long, 8 to 11:40 probably. Unless they say we don't need more, and we'll stop a little early. But then, so I only have a little bit of office hours between my two classes. Then I have 12 to 3:30. So from 3:30 until 5:15, I'm free. Okay. All right. Okay. Shakina is here. Charity did call in today, so she may be sending something. Courtney Humes is still here. Ambry is still here. Essence is still here. Ryan is still here. Larius hasn't made it in yet today. Monique is still here. Sasha is still here. Allison's still here. Darius is still here. Scarlett just left, but I'll give her credit. Okay, Will is still here. Brianna hasn't made it in at all today. Naya hasn't made it in yet today. Maria hasn't made it in yet today. And Dakota, surprisingly, hasn't made it in yet today. Yes. I'm thinking not, because we are at bimetallic strips now, and we've got ideal gas law to do, and we have kinetic theory of gases to do. So, yeah, we're not going to have time for that today. I should wait till the end of the class to call the lab roll. Yeah, I assume it's still working. It's sort of a crappy old staple. Good deal, thank you. Okay, back to the bimetallic. Y'all, yes. Do I have the final one? Yeah. Pardon me? Are you not going to be here Monday? Pardon me, I can't hear.
I'm not sure yet. I have to volunteer and I may be there all day to class, so I'm not sure.
Okay. Well then after class, yeah, I've not got it anywhere close handy right now, but I can get it after class because we're not anywhere close to needing it yet. So, do we need to take a real quick break? Would that be, no one needs a break? Okay, we'll keep going. I was getting awfully dry mouth, but we can manage. Okay, so here we have applications of thermal expansion to bimetallic strip. Here is the atypical bimetallic strip. Brass on the bottom, steel on top. Doesn't matter whether you put it top or bottom. At room temperature, it's going to be right about here. But as you increase the temperature, the brass has a higher, if you look at the table, we were just talking about, table of thermal expansion, 19 millionths per degree, whereas steel was 11 millionths per degree. A little bit of a difference there, but it's still in talking about millionths of a meter or whatever centimeter per degree. So if you make it long enough then and fix one end, the other end bends up. Put an arrow on here and have that at room temperature, and there goes your higher temperature. And you can calibrate it that way. A lot of the thermometers that have the point on them, that's how you read temperature, bimetallic strip down here. That's how it does it. It starts here, or it goes up, or comes down, because the brass has a higher temperature, but they're fused together, so the steel doesn't expand as fast, so the brass has to go up around it. Now, what else they do to it, they coil it in a coil, fairly tight coil, so you can get a really long strip, so that the degree, it doesn't take much thing because they got it in a coil, and then you get a really sensitive reading on it. Thermostats use, the old ones anyway, use bimetallic strips. Okay, two metals expand differently, since they have different coefficients of expansion, but they're fused together, so one of them has a bend. One of the higher one bends around the one with the lower one. And that's how you get it. And there's a picture in your text. Let's see if it shows it here. No, it doesn't. In your text of that, you see that strip in there. And the trouble is, the way they drew it, the bottom picture in the book, okay, because they wind it real big to begin with, then when it heats up, it's the brass is pushing the other one further out. The iron doesn't contract as much, so they do show the picture here. So the one in the book, I said, that looks like iron on the outside and brass on the inside, and that's probably exactly what it does, because your needle goes in the other direction. All right. Then there's also area expansion. Two dimensions expand according to a change of area. Delta meaning difference, A minus A original, okay? And this is a coefficient of area expansion. That's the gamma. Alpha was the coefficient of linear expansion. Gamma is the coefficient of area expansion. And that would then be gamma A naught. And this is wrong. That's got to be delta capital T, not delta little t. Yes, that is wrong. There's a little t stands for time, not temperature. So that's a capital T there. And by the way, since area is linked by width, the gamma comes out being twice the alpha. The coefficient of area expansion is twice the coefficient of linear expansion. So, and this is a really exaggerated situation there. If you had a washer at normal temperatures, it would be that, and you put it over a flame, everything expands, and including the hole in the middle of it, that expands, this expands, and the thickness expands too. All of it. And here is, second? Yeah, no, I got you. I thought you were saying something too. Yeah. Okay. So there is your coefficient of area expansion. And that was also listed under Applying Physics 10.1. Okay. There is also a volume expansion, but before they get to that, they do example 10.4, rings and rods, and you can certainly take a look at that one. And here's your coefficient of volume expansion. Now, why they did, and here's FA. Why they chose to do their Greek letter, the symbols, the way they did, I haven't quite figured out yet. Okay? I would have thought if alpha was linear, beta would be area, and gamma would be volume. But no, they did alpha linear, gamma area, and beta volume. So I don't know. I don't know why they did it that way. So delta V is equal to beta, which is your volumetric change, times V0 times. And there they did it again. That should be temperature, not time. So that's a capital T there as well. Okay? And for solids, three-dimensional solids, beta is 3 alpha. For liquid, the coefficient of volume expansion is given in the table, and they don't have a linear for liquids. And you don't have an area for liquids. You only have the volumetric expansion. But they don't give a table for the other two. If you're doing area for solids, just double that. If you're doing volumetric for solids, triple it. Okay. Okay. Now, there's more applications of thermal expansion that I don't see in the text, so I'll go over these pretty quickly. Pyrex glass, the thermal stresses are smaller than for ordinary glass. You look back at your table. Do they list Pyrex glass? Yes. Ordinary glass was 9 millionths per degree Celsius, whereas Pyrex was almost a third of that, 3.2 millionths, okay, per degree Celsius. So in other words, Pyrex glass doesn't expand and contract nearly as much as regular glass does. What's an application or implication of that? Would you stick any glass dish in an oven and cook in it? No, but you can Pyrex, because Pyrex has a smaller coefficient of linear expansion. Similarly, this, actually, I remember my wife did this, even though I warned her not to. She had bought these neat little decanters at a antique store. Didn't pay too much for them. They just were really pretty. They weren't quite cut glass, but they were really nicely done. And she was going to put up some hot peppers and vinegar. And they had the little stoppers for them, and so that, they'll be fine. And she had boiled her vinegar and had it very, very hot. And she had put the peppers in there, stuffed them in pretty well, and then went to pour the vinegar in. I said, you probably should put the thing in a hot water bath first, because that glass is, it probably can't handle this change of temperature. No, I think it'll be okay. Poured it in, pop. Okay. Broke the glass, broke the decanter shed, ruined the peppers, ruined the vinegar. It was a big deal, but then she put the other, she had 3 of them, so she put the other 2 in a bath, hot bath, and then poured the vinegar in, and they worked fine. So, physics is nice to know. Okay, but you don't rub it into your life. Okay, now that's nice to know too. All right, quick quiz, 10.2. All right, here, let's do the second one here. Sea levels. Warming the oceans will increase the volume of the ocean. That is true, but really what changes the volume of the ocean more so is what? Or in addition to this, I won't say more so. Okay, warming the oceans will increase the volume of the ocean. That is true, but what also contributes to sea level rise? Huh? Okay, yeah, that's always there, the tides, yeah. But what else will make the sea level rise?
The melting.
The melting of the ice. Now that water is going into the oceans as well. So there's twofold. You got water going in, and you have, because the water is warming, it also expands. So you have twofold reason. When my wife had professional meetings over in Rome one year, several years ago, and it happened to be right at the breaks between my terms, so I got to go. No, actually, it was a Christmas break, Thanksgiving break. So I took a couple of days off at Thanksgiving, 3, I guess it was, and while she was over there in her meetings, and we went, in addition to see some friends in Italy, we went to Venice. And already then, Venice, which of course doesn't have many roads in Venice, right? They have canals, because it's a series of islands and other things. And already they said many buildings could not use the ground floors. They were now basement pools, so they were up on the next level because sea level was rising. There are towns in Florida built right on the beach that have been fighting that rise already, and their main streets flood pretty regularly, and businesses have been wiped out. Homes have lost the beachfront because the homes are the beachfront now, because the water is indeed rising. So a lot of these people will say there's no such thing as global warming. Well, whether there is or not, the sea levels are rising. And I don't know why it would be if the sea levels rising if it's not. Well, they say it's just normal increase in temperature, but whatever. And by the way, this has nothing to do with that, but it just reminded me because that is a little bit of a political thing. I don't know if I said it in your class. I wish I would have said it before everybody left. 2 things, actually. I think I may have said the first one earlier, but some of you have come in since. But here's the one I forgot to say. If you are not registered to vote, I take it all of you are more than 18 years old, right? Any of you less than 18? Okay. You're eligible to vote. If you are not registered to vote, please register before Monday or by Monday, the 31st. Otherwise, you will not be able to vote in the primaries for the senatorial seat that's up for grabs. Remember, when Sessions became Attorney General, we lost our Bentley, then appointed rather than having him elected, Strange. And when Governor Ivey came in, she said, no, we need an election. So the primaries have been set for the 15th of August. So you'll have to be registered by July the 31st. Now, any of you live in the city of Birmingham? You do. Okay? The elections for mayor, city council, and board of education are the very next week, the 22nd of August, and you have one more week to register for that. But if you register by the 21st, you get to vote in both elections. If you wait till after the 31st, then you can only vote in the mayoral or the city elections. Please register and please vote, folks. Not telling you how to vote, but please vote. It angers me no end to see people getting elected with only like 40% of the registered voters voting. That means the winner may have only 21% of people voted for him or her, and they've won the election on just 1/5 of the vote. And then what's more, there's a bunch of people eligible to vote that aren't even registered. So it's even less. I mean, we have a minority government in just about every area. We should have a majority. Democracy is based on a majority. Please vote. And I put it this way. You don't vote, you forfeit your right to gripe, okay? If you like to gripe about things, vote. Then if the other party wins or other nominee wins and they don't do what you want them to, you have a right to gripe. If your candidate wins and he or she doesn't do what he or she promised to do, you have the right to gripe. But if you don't vote, to me, you don't have that right. Just zip it, because you had your chance. Vote. Please vote, folks. Please vote. Okay. So, now, before we get into the unusual behavior of water, we have some quick quizzes. The first of these: if you quickly plunge a room temperature mercury thermometer into very hot water, the mercury level will go up briefly before reaching a final temperature, final reading, go down briefly before reaching a final reading, or not change. Okay, it certainly will go up, but it first goes down. And why would that be? It first goes down, then it goes up way high, but it first goes down. Why? What is in thermal contact with the water? Not the mercury. The glass. The glass expands, actually dropping the mercury level until the mercury gets in thermal equilibrium with the glass, and then it goes up. So you got two things. You got glass heating, then you've got the mercury heating. So the first reaction is actually for the level to go down briefly before it climbs at the end. Let's see if they got it right here. Yep, go down briefly before it starts going up. 10.3. If you're asked to make a very sensitive glass thermometer, which of the following working fluids would you choose? Mercury, alcohol, gasoline, or glycerin? If you want a very sensitive glass thermometer.
What is glycerin again?
Second?
What is glycerin again?
Glycerin is another liquid. What you have to do is go back to your table, which, do any of you have your tables? Ryan does. Do you? Is that your text? Go to page 327. There's the table. And what do you want? If you want a very sensitive, do you want a high coefficient volume expansion or a low coefficient volume expansion?
High.
You want as high as you can get, okay? And which would be the best out of, mercury, alcohol, gasoline, or glycerin? Mercury, 1.82. Gasoline, 9.6. Glycerin, 4.85. And alcohol, 1.12. Yeah, it looks like gasoline would be the best. Strange, but true. Do they use much gasoline in it? I don't think so. Why? Second? It is flammable, so if you were to break it, especially around heat, you could have a fire. Also, gasoline, you would have to color it pretty much, because otherwise you don't have a lot of distinction. Or you do that to alcohol too. You put usually a red color in that. Okay, so anyway, you're right. Gasoline would be it. 10.4. Two spheres are made of the same metal and have the same radius, but one is hollow and the other is solid. The spheres are taken, made out of the same metal and have the same radius, but one is hollow, one is solid. The spheres are taken through the same temperature increase. Which sphere expands more? The solid sphere, the hollow sphere? They expand the same amount, or there's not enough information to say? Which do you reckon? Which do you reckon?
C.
Second?
C.
I can't hear.
C.
No, it's not what metal. They're the same material. Okay? Which would expand more, the hollow or the solid?
The hollow.
Why?
Because wouldn't they expand the same?
Okay, the hollow because they would expand the same, huh? No.
Yeah, I'm
Okay.
saying, wouldn't they expand the same?
Now, actually, the hollow acts like an area expansion, right? Where the volume, the solid act like a volume expansion. Remember, the area expansion is twice the linear, the volume expansion is 3. So it should be the solid. Let's see if that's what they got. That's 10.4. I'm guessing A. 10.4. It actually says they expand the same. Huh. Yeah. I am not certain I agree with that, though, but we'll let it ride. Okay. Part of that would depend on how thick the hollow one is, you know, but we won't go there. Okay. And then 10.5. There's global warming and coastal flooding, which we saw here. Quick quiz 10.5. Why doesn't the melting of ocean-based ice raise as much concern as the melting of land-based ice? Let's say the North Pole. The North Pole is ice, but that's over water. It's floating ice. Antarctica, on the other hand, is mostly land-based ice. There probably is some shelf ice out there that's melting. That doesn't affect the rise in temperature as much. Why?
The ocean is changing.
What's that?
The ocean is changing temperatures, isn't it? Like the ocean can be
For
warmer.
both of them, yeah.
But if Antarctica warms, and that's land, isn't it? So
Okay. Well, if Antarctica warms, the ocean has to be warming too, you know. But yeah, you got a good thought there. But here's why. Guess what? The water-based ice is already in the water. So when it melts, you know, actually, as we'll learn in the next section, it actually takes less volume than it did when it was solid. Okay? So actually, it doesn't change it much at all because it's already in the water. It just changes from ice to water. Just picture this. You have a glass of iced tea or ice water. Lots of cubes of ice in it. When it melts, does it overflow? No, the ice is already in there. But if you had a chute here leading down to your glass and it was full of water, and as the ice melts and drips in, it would have to overflow, wouldn't it? So if it's already in the water and melts, it doesn't change the sea level as much. It's only the land-based ice, the glacial ice over land, when it melts and goes into the sea, that's what makes the big difference. Let's see if that's what they say. That makes sense to me. Unlike land-based ice, ocean-based ice already displaces water, so when it melts, the ocean levels won't change much. Very good. Now we get to the very, very, very unusual behavior of water. Water has to be one of the strangest compounds on the planet. And if it weren't, we'd be dead. We depend on some of this strangeness. Water has several unusual behaviors. Number one, it shouldn't be a liquid. The molecular mass of water is oxygen is 16, hydrogen is 1 each. That's 18. No other molecule that I know about with a molecular mass as low as 18 is a liquid at normal temperatures and pressure. They're all gases. Oxygen is 32, not 18. Nitrogen is 28, not 18. Carbon dioxide is 44, not 18. They're all gases, and their water's a liquid. Now, hydrogen is 2, yeah, it's lighter. And helium is 4, that's lighter. But yeah, most things with molecular weights as low as 18 are gases in normal conditions. Water, unusual. Okay? Water also has that enormous surface tension. We saw that in the last lab, right? they couldn't get that to overflow, right? Until he kept pouring water in because that surface tension held it on the top. Water is really unusual, okay? Here's the deal. As the temperature of water increases from 0 to 4 degrees, it actually contracts, okay? This is showing the density of water, not the volume of water, but so the density is exactly inversely related to the density, and density inversely related to volume. But above 4 degrees, the water then exhibits an expected expansion with increasing temperature. Okay? So what's going on here? Remember, water has that strong hydrogen bonding, so those water molecules, when they're liquid, they stay really close together. But then as the temperature drops and they start phasing into being a crystal solid, then it actually has to push the molecules further apart to get them to fit in the crystal. So the density actually goes down. So as you're cooling water, the density increases until it gets right around 4 degrees, then it's the maximum density, and then as it starts freezing, the volume increases so the density starts falling off again. Okay, above 4 degrees it exhibits the same. The maximum density of water is 1,000 kilograms per cubic meter at 4 degrees Celsius. 0 degrees Celsius is awfully close, but not quite the same. Okay. Now, what difference does that make? Any? It does. Surface of the earth is covered mostly with water. Okay? Now, think of the ponds, the lakes, the streams, rivers, the oceans. Okay? Now, generally, if water did what other materials do, and when it cools, it contracts, and when it freezes, it continues to contract. If that were the case, then when water froze, it would freeze from the bottom up. Because the denser water would move to the bottom as it continues to cool, it would freeze, 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 freeze. All life, major life, would die. Fish, anything that, as it is, water when it freezes, is less dense than water, and it rises. So then you always have this air gap between the water and the ice, and that air gap allows things like seals, whales, porpoises, anything that's really breathing air, they can actually come up under the ice and still get oxygen. Okay? And the fishes and other things like this, they can swim around in the water and they don't get frozen to death. And it literally would freeze from the bottom up if it didn't have this unusual behavior. If they couldn't live, guess what? We don't live. We're all a fairly sensitive biosystem. And thank you, water. Leaves is strange, huh? All right.
Isn't there like also like a thermocline?
What's that?
Isn't there also like a thermocline of water to where like it'll switch at one point to where like the bottom is hotter than the top? Or, like, or the bottom is colder than the top.
Yeah, that's exactly it. Yeah, that also contributes to that, which is nice to have because that water down there, they can continue living and don't freeze to death. Yeah, you're absolutely right. All right, let's move to 10.4, the ideal gas. Okay, the ideal gas law. Let's first define what an ideal gas is. If a gas is placed in a container, unlike a liquid and unlike a solid, the gas molecule is free to move, they take up the whole container. Okay? It expands to fill the container uniformly. Okay? Its pressure will depend on the size of the container, the temperature of the gas, and the amount of gas in there. So all these things contribute to pressure. Now the pressure volume, size of container, the temperature, and the amount of gas are all related to each other by an equation of state. And here it comes. No, not yet, okay? Thought they were going to say it, but they're not. The equation of state can be complicated. Yeah, what can't be? It can be simplified if the gas is maintained at a low enough pressure. If you start getting gases at too high pressures, stranger things start happening. They're too high pressure that you're forcing the molecules closer together. You may have some sticking going on and stuff like that. So if you maintain a low enough pressure, it acts like you expect it to. Most gases at room temperature and pressure, which are fairly low pressures, behave approximately as an ideal gas. So what is an ideal gas? It's a gas that's appropriate, it's behaving properly, okay? Okay. So what are the characteristics of this ideal gas? A collection of atoms or molecules that move about randomly. Now, what do we mean by that? Basically, they hardly ever are in touch with each other. Okay, if they are, it's just a random collision, and then they bounce back elastically from that. Okay? If you've got too high a pressure, like I was saying, sometimes those molecules, when they run together, they stick, or they don't bounce as freely. You don't have conservation of energy or momentum if there's too much pressure. They exert no long-range effect or long-range force on each other. Like I said, when they collide, they just elastically bounce off each other, and there's no sticking and no even attraction between them. This molecule couldn't care less something's out there. It's not really attracted to it in any way, shape, or form. Each particle is individually point-like, occupying a negligible volume itself, but the whole, they occupy the entire volume. So in other words, for the volume of the actual atom or molecule is tiny compared to the volume of the space it's occupied. So most of it is empty space in between. Okay. Now, a little bit of a definition before we can get to the ideal gas law. Okay? What do we care about these furry little blind creatures that crawl under your grass? Nothing. That's not the moles we're talking about. Okay? What we're talking about here is convenient to express the amount of gas in a given volume in terms of the number of moles that it has. And you can think of moles as an abbreviation for molecule. Not quite the same, but that's how I like to think of it. Okay? So, the number of moles, N, is the total mass of the material divided by the molecular mass. This is total mass divided by mass per molecule, okay? And that the masses cancel out, look over the molecule, and N is moles, which basically is referring, in some sense, to molecules. 1 mole is the amount of the substance that contains as many particles as there are in 12 grams of carbon-12. What? Why? Okay. Here's the deal. When we say carbon-12, we mean carbon that has a total of 12 protons and neutrons. 6 protons, 6 neutrons. Total of 12. So its mass is going to be 12, okay? 12 atomic mass units, or just, they call them now mass units, okay? Or just units. And that's what we use as a standard. So oxygen would have about 16, okay? Nitrogen right at 14. You know, that would be the number of grams of nitrogen that would have the same number of particles as 12 grams of carbon. So in other words, you're getting down to how many moles or molecules you have of that material. So you take the mass and divide it by the molar mass, which is also the molecular mass. Okay, mass per molecule. Now here's a character who was way ahead of his time. Okay? This is getting into a little bit of chemistry, but not bad. You need it in physics too. Remember, good old Aristotle said there's only 4 elements. Anyone remember what they were? Aristotle's 4 elements? Second? Earth?
Air.
Okay. He called it wind.
Water, wind, water, and fire.
Fire. 3 of those made a singing group. You remember?
No. What?
Made a singing group.
Earth, wind, fire.
Earth, wind, and fire. Okay. Add water, and you got the 4 elements of Aristotle. I'm sure that's how they named their group. I bet you it probably has something to do with it. But anyway, and because he said everything else is made up of these materials. Well, some clever little guys about 1,600 years later said, hey, if that's really true, then we should be able to take certain quantity of earth, which is really cheap, air, which is really cheap, water, which is really cheap, and heat it and cool it and mix it and grind it and put different proportions in. We should be able to come up with pure gold, shouldn't we? And make us a ton of money. Or silver, or bronze, or copper. We can make anything we want to if we get the right ratios of earth, air, water, and fire, or heat. So here came the alchemists, and they started studying and putting together these things, and they found out after a very short time they better keep really careful records. How much they did so they wouldn't have to repeat the experiment, and they tried all different combinations and various things with it and stuff, and as they did this, they found out that things did combine by what they called the law of definite proportions. If you had, name me a number, 30 grams of oxygen or hydrogen. Oxygen. 30 grams of oxygen, and say me another amount of hydrogen. 15 grams of hydrogen, okay? And you found out that for every 2 grams of hydrogen, 16 grams here. So you're going to use up the oxygen and still have plenty of hydrogen left over, because they always combine with law of definite proportions in mass proportions. That was beginning of the atomic theory. And they were really studying that. But what really threw a wrench into their ideas, they found out that when you combine volumes, give me how much nitrogen you have?
3 liters.
3 liters of nitrogen. And how much hydrogen did you have?
4.
4 liters of hydrogen. Okay? You combine those and made ammonia. Okay, guess what? It took 3 liters of hydrogen to combine with only 1 liter of nitrogen. And guess how much ammonia you made? 3 liters of hydrogen, 1 liter of nitrogen.
4.
1 liter. So the volumes did not combine. They combined by definite proportions, but they were nothing as reasonable as the masses were. The masses made perfect sense. You had conservation of mass. You don't have conservation of volumes. And people said, why not? Well, along came a guy named Avogadro. Sounds like a good Irish name, doesn't it? I think he was probably Italian, but I can't remember for sure. And he came along and made this proposal. Well, what if, and by the way, they also noticed this, a liter of hydrogen was much lighter than a liter of oxygen, which was lighter than a liter of carbon dioxide. But it was heavier than a liter of nitrogen. So they had different masses, different weights, okay? And they were studying those two, and they combined at different proportions that were really weird. So what was going on here, Avogadro said, well, what if every liter of gas, no matter what gas it is, had the same number of molecules. And they said, are you nuts? Why would that be true? You know? And they dismissed him. Poor Avogadro, I think, died, was buried, and probably 20 to 50 years later, they said, you know what? I think he was right, okay? I don't think he ever realized that his theory, which was ridiculed and tossed about and made fun of and ignored, turned out to be absolutely right. And Avogadro's number, they named the number after him, the number of particles per mole, which is the molecular weight in grams of that substance, is 6.02 times 10 to the 23rd particles per mole. This isn't just gases, it isn't just liquids, it isn't just solids, anything. 6.02 times 10 to the 23 particles makes up one molecular weight of that material. As defined so that 12 grams of carbon contains Avogadro's number of atoms. Okay? The mass of an individual atom can then be calculated as the molar mass, say 12 for carbon, divided by Avogadro's number. That gives you the mass of a carbon atom. Whereas the molar mass of oxygen, which would be 16, divided by that same Avogadro's number, would be a bigger mass, of course. Okay? So the mass of the individual atom can be calculated. Now, those would be tiny little masses because that's such a huge number. 10 to the 23, that's a pretty big number. All right, so Avogadro's number and masses, the mass in grams of one Avogadro's number of an element is numerically the same as the mass of one atom of the element, expressed in atomic mass units. Now, we used to call these AMUs for atomic mass units, now we just call them U's. So, in U's, in that unit, the atomic mass, and that basically is talking about number of protons and neutrons, basically. So 12 U would be, carbon has a mass of 12 U's, 6 protons, 6 neutrons, 12 U, okay? But it has a atomic mass of 12 U and a molecular, and a molar mass of 12 grams. So 12 grams, the same number is used, but the gram would represent the Avogadro number, whereas the U's will represent single atoms. So 12 grams of carbon consists of Avogadro's number of carbon atoms. The 12 U's of carbon would be a single carbon atom. That holds for molecules as well. You do molecular masses like carbon dioxide is 44, I believe. So that 44 grams would make 1 liter, well, 1 liter of carbon dioxide. But 44 U's would make 1 molecule of carbon dioxide. So now we can look at the ideal gas law. And they just pop it on us here. And this is on the top of page 334. PV is equal to nRT. Okay? Now, P is the pressure. Okay? Now, I don't know if you remember, pressure has an awful lot of units. Okay? You can talk about pascals, kilopascals, PSI, atmospheres, bars, torrs. There's a ton of different units for pressure. Let's just forget that for now. Volume, there's a ton of different volumes. Cubic meters, cubic centimeters, cubic feet, cubic inches, cubic miles, whatever. Cubic furlongs, I don't know. Okay? But this formula is written here, but typically we'll use SI. So that pressure would be in pascals, the volume in cubic meters. N is your number of moles, okay? R is your universal gas constant, okay? Universal gas constant. And that R, okay? The R in This would be your standard SI unit. 8.31 joules per mole K. Okay? In atmospheres, if you're measuring not Pascal per atmosphere, it would be 821 liter atmosphere per mole K. Okay? It's the equation of state for an ideal gas. That is the equation of state for an ideal gas. Temperatures used in the ideal gas law and just about every other law have to be kelvins. Have to be kelvins. Because guess what? If you put degrees Celsius here and you drop that below freezing, which would be not a hard thing to do, then you either wind up with a negative pressure or a negative volume. You can't have either one. Okay? So these have to be an absolute temperature, meaning Kelvin. Okay? So you notice there's no option here that you do anything other than Kelvin. Okay? What you use for P and V, yeah, that's going to change this constant because those can take on various values. But you've got to use temperature in Kelvin. The others are just numbers, a constant or number of moles. Now, there's some alternate versions. PV is equal to capital N kV. Now, let's see. Remember, little n was number of moles. Capital N is number of molecules. If you use that, then rather than the ideal, the universal gas constant R, what we'll use is Boltzmann's constant, which did we run into this in this class, or was it the other class? Boltzmann, have we hit Boltzmann's constant? I don't recall that we did. That was in the other class. That's Boltzmann's constant, K sub B. By the way, if you have a book, look at your front inside, nope. Yeah, front inside cover. No, not there. Back inside cover. These different books have them in different places. Let's see if this is right. Back inside cover, not on the very last, the actual cover itself, but the next page in there is your physical constants. And there's Boltzmann's constant is number 3, Avogadro's constant number is number 1. Universal gas constant, the very last one there, and with the units given. So you see all these constants are listed in that table at the back. So here's one. When you're using number of molecules rather than number of moles, use Boltzmann's constant. When you're using number of moles, use universal gas constant. Here's another one. Oh, and by the way, this little n is capital N, total number of molecules, divided by Avogadro's number. That gives you how many molecules you have. I mean, how many moles you have. Little n is number of moles, capital N is number of molecules. All right. Here are the assumptions in the ideal gas law. Okay? Trying to find them in the book. I don't see them right where I expect to see them, but they may have already occurred. I'll let you find them if you need them. Here's the assumption. The number of molecules in the gas is large, of course, and the average separation distance between them is extraordinarily large compared to their dimensions. Okay? That gets to the thing of the pressure being relatively low. At very high pressures, you're forcing those molecules closer and closer together. You lose that assumption. Then the ideal gas law. Oh, wait, I'm sorry. This is kinetic theory of gas assumption. This is 10.5. And here are these assumptions. Bottom of page 337, top of page 338. The first one, the number of molecules, the kinetic theory of gases. Number of molecules in a gas is large, and the average separation between them is large compared to their dimensions. The molecules obey Newton's laws of motion, but as a whole, they move randomly. Okay? Newton's laws of motion say, if these molecules are moving in a straight line, they continue in a straight line unless they're acted on by an unbalanced force, which usually is a collision with another one. Okay? If there is an unbalanced force and that force acting on them, then they change their acceleration. Okay? And the force with which one hits the other is the same opposite as the one force of the other hitting the one. So Newton's laws of motion are obeyed. The quantum mechanics, you don't have to get into that for this case. Okay? More. The molecules interact only by short-range forces during elastic collisions. No sticking together, no lingering and stuff. They're elastic collisions. They interact only by short-range forces during those elastic collisions. And once they collide, they bounce off with no loss of kinetic energy and no loss of kinetic energy is conserved, and so it's linear momentum. The molecules make elastic collisions with the walls of the container, whatever that container is. The container be a jar, the room, your tire, or something like this. Now, when you get really high pressure in your tire, maybe things fall apart. All molecules in the gas are identical. That is the assumption. How many gases do you know that that's the case? In this room, mostly nitrogen. A great number of oxygen. Carbon dioxide, methane. Who knows what all other gases are in the room. So the room air won't be purely an ideal gas, but it'll act a lot like an ideal gas because it's predominantly nitrogen. Did I mention carbon dioxide and water? I think I did, but whatever. So let's look at the pressure of an ideal gas. This is 10.5.1 in your text. Okay? The pressure is proportional to the number of molecules, of course. If you have a fixed volume and you put more molecules in there, you got to increase the pressure. Okay? So it's proportional to the number of molecules per unit volume and also proportional to the average translational kinetic energy of the molecules. So here's what that's saying. The pressure is proportional to, and by the way, the constant proportionality is 3/2. Surprise, surprise. Just a perfect number like that. To the number of molecules per unit volume, that is capital N per V, standard SI units, and the average translational kinetic energy of the molecules. And that would be 1/2 m V squared, average V squared. Okay? Rather strange way to put it, but that's how they do it. Average kinetic energy, molecules per volume, proportional to it with a constant proportionality 3/2. Okay, so here's the gas molecule moving with a velocity v up this way, hits the wall, okay, and then it veers off the wall with a certain elastic reaction, okay, and then continues moving, okay. You break that down into a horizontal component and a vertical component, and you move from there. Actually, it has 3 components: horizontal, vertical, and X component, Y component, and Z component. Okay, they only show the X. Don't know why. It looks like it's well, of course, it's parallel to the X-axis. The Y component would be parallel to the Y-axis. The Z component parallel to the Z-axis. Okay. The pressure is proportional to the number of molecules per unit volume and the average translational kinetic energy of the molecule. That's exactly the same sentence they have here. Why did they repeat it? I don't know. Pressure can be increased how? Increasing the number of molecules per unit volume, of course. Pump more air into your tire or into the basketball or football or volleyball, you get greater pressure. increasing the average translational kinetic energy mode of the molecules. How do you do that? Heat them up. Okay? If you heat up the increase the temperature of a gas, it's going to increase its pressure if the volume is fixed. That's why a pressure cooker works, or how a pressure cooker works. You put more heat to it, you don't let any of the steam escape, so the pressure builds in there. You monitor that, and as soon as that pressure starts getting too much, you turn that heat down. Otherwise, you're going to have a pretty big explosion in your kitchen. Not going to be a pretty sight. Okay? Now, the molecular interpretation of temperature, they call this, let's see, was that still? Yeah. Still 10.5, but in this text it's 10.5.2. Molecular interpretation of temperature. Temperature is proportional to the average kinetic energy of the molecules. Proportional to that. Temperature is a direct measure of the average molecular kinetic energy of the gas. The average molecular kinetic energy of the gas is this 1/2 mv squared. Okay? And that's the average v squared, too. Now, the m would be the molecular the mass of one molecule of that gas, okay, by the way. And that proportionality constant, there's our 3/2 again, but it also involves this Kb, Boltzmann's constant, and then times the temperature. So the temperature is a direct measure of the average. It's proportional to average kinetic energy. Here's the average kinetic energy. The temperature is proportional to that. Here's the constant proportionality. 3/2 still there, but Kb, Boltzmann's constant, is also included. 3/2 Boltzmann constant. The total translational kinetic energy is proportional to the absolute temperature. The absolute temperature. So this total, not just average, but the total kinetic energy of that gas is equal to, is proportional to the absolute temperature. And remember, every time you see a capital T in any of these formula, you know that is Kelvin. The only exception to that, if you see a delta T can either be Kelvin or Celsius because they're the same sizes. Okay? So the difference is just going to be the same difference. So this is proportional. Now your constant of proportionality is 3/2 nR. Okay? That's the total kinetic energy, and this is 3/2 nRT. Okay? What else do we see was nRT? PV was nRT. So obviously, 2/3 of the total kinetic energy is equal to PV. Or at least that's what it appears here. Okay? Now, before we move on, here's a quick quiz, 10.6. One container is filled with argon gas and another with helium gas. Two containers, one with argon gas and one with helium gas. Now, I don't know what they mean by filled with, because you put any amount in there, it's going to fill the container, okay? But we'll just take them at the word here. Both containers are at the same temperature, okay? Which atoms have the higher root mean squared speed? What do we mean by that? Well, obviously, they left off some units here. Left off some things in this thing. Let's see if we can pick this up. Ha, here we go. We need this information first. So let me see. Maybe we should do internal energy. Oh, yes. We're almost at the end of the chapter. So here's the internal energy. That was just stuck in here. Not going to have time for a lab, but we sure do have time for go, I'll be able to go and give you your test here. Okay. Internal energy. Now, in a monatomic gas, what do you think they mean by that? Single what? Single atom per molecule. Name some monatomic gases. No, hydrogen's a diatomic. It's always H2. Anyone know? Look at the last column. Your noble gases: helium, neon, argon, krypton, xenon, and radon. Okay? Those are all monatomic gases. They have filled outer shells. They don't combine with anything. They float around by themselves and don't combine with anything. All your other gases, pretty much, hydrogen is H2 diatomic, nitrogen is N2 diatomic, oxygen is O2 diatomic, fluorine is F2 diatomic, chlorine is Cl2 diatomic, bromine is Br2 diatomic, iodine is I2 diatomic. Okay? Those are most of your other elemental gases, and of course, your molecular gases are never monatomic because they're CO2, NH3. They got to have other things in them because they have two or more atoms, two or more elements. Okay, so they got to have at least one atom each. So for a monatomic gas, which basically are your noble gases, helium, neon, xenon, radon, argon, those things, krypton. The kinetic energy is the only type of energy the molecules can have. They don't have any vibrational energy because there's nothing to vibrate with. They don't have any rotational energy because they don't have anything to rotate around. Okay? So they only have this, so your internal energy, the total internal energy of these monatomic gases is your 3 halves nRT, which is exactly what we saw here was the average total kinetic energy of the things, because that's all your energy. The Ke is the only type of energy, so that's the U, the total internal energy of the gas. In a polyatomic gas, that could be diatomic or many atoms in it, additional possibilities of contribution to the internal energy are rotational, vibrational of the molecules, so those can be in there too. But it's more than just kinetic. Okay? So, how do we talk about the speed of a molecule? Well, let's go back to this equation right here. 1/2 mv squared is equal to 3/2 kBt. The average kinetic energy of a molecule is 3/2 Boltzmann constant times the absolute temperature. Okay? Well, let's multiply both sides of the equation by 2. Wipe out the 1/2 in the denominator. So now you have mv bar squared is equal to 3 kBt. Then divide both sides by m, and you have v squared is equal to 3 kBt over m, and then take a square root, and let's see what you get. There it is. The velocity, the root mean square of velocity of a molecule is 3 kBt divided by m, take a square root of it. Okay? If you don't like kb, and you don't like this m was the molecular mass, then go to 3 RT divided by the molar mass. Okay? Let me make sure I said that right. They don't say it here. Let me go back and make sure. I don't think they ever say it. Yeah, the little m is the atomic mass, and I don't think they ever list the capital M, but I'm pretty sure that is the molar mass. Let's make sure that's right. Yeah, where capital M is the molar mass in kilograms per mole, not grams per molecule, but kilograms per mole. Big M, okay? Whereas little m is your mass per molecule. Okay. So Boltzmann constant goes with molecular, and universal gas constant goes with molar. Okay. So here are, okay. Let's go back. Okay. Here's our table. Some root mean squared speeds. Okay. Hydrogen, because it's such a lightweight gas, it has a very small molar mass. I was always saying 2 is a little more than 2, but not much. 2.02 times 10 to the minus 3 kilograms per mole. That's a capital letter M. And then your root mean speed is 1902 meters per second at 20 degrees Celsius. That is flying, folks. That's almost 2 kilometers a second. Hydrogen gas flies through there, okay? Helium, which is twice as massive, isn't quite half the speed because it's v squared, so the square root of that would be 1352. Water, which is 18 times 10 to the minus 3, that's 637. Neon, which is very light, but just a little more massive than water, 602. Nitrogen and carbon monoxide, 28 in 2, and that would be 5 to 11. Okay, I always get confused on the names. I think this is nitrous oxide, 30, and that's 494. Oxygen, which is 32, 478. Carbon dioxide, 44, 408. Sulfur dioxide, pretty heavy, 64.1 times 10 to the negative 3 kilograms per mole, and that's 338 meters per second at 20 degrees Celsius. Okay. That leads to our quick quiz. Okay. Yeah. One container, okay, here's what I was starting to do before. One container is filled with argon gas, another with helium gas. Both the containers are at room temperature, at the same temperature, not room, but same temperature. Which atoms have the higher root mean square speed? What do you think? Argon is A, helium's B, C, they have the same speed, D, not enough information to say. What? B, helium, because the lighter the mass, the greater the velocity, because they have very similar kinetic energies. And that, sure enough, was B. You got it. Toyota. Okay. One of the last slides here, Maxwell's distribution. Okay? I believe this is James Clark Maxwell who did the tied together magnetic and electrical forces and how the fields and things like this. Brilliant character. I didn't know he did that much with ideal gases, but these guys did a lot in various areas. A system of gas at a given temperature will exhibit a variety of speeds. Of course it will. So we can talk about the root mean speed, but that's mean, okay? So the three speeds are of interest. The most probable speed, the average speed, that's not necessarily most probable, and the root mean squared speed. Okay? The area under either curve is equal to n, the total number of molecules. In this case, n is equal to 5. So here we have two gases at different temperature. Identical gases, same number of molecules, that's n. Okay? Same number of molecules at each one. Okay? Area under these two are the same. So when you spread out, increase the temperature, you have to reduce your heat. So you have a wider spread of your velocities. Okay? Always, the most probable velocity, which is the peak velocity, or awfully close to that, is less than the average velocity, and that's always less than the root mean squared velocity. Okay? So most probable is one that occurs most of the time, because this is it's this velocity here, which is the one occurring most of the time, most probable. Average will be over here, because always you have a fix. This is going to be 0 here. This tail extends out, so you always have a little bit of shift here that pulls up your average velocity, and the root mean squared velocity is even greater than that. Okay? On this lower temperature, the most probable is at the peak. The average won't be far off that, and the root mean squared not far off that, so they'll be closer together because the peak is pretty narrow. The wider the peak, the farther apart they get as well. Okay? Any questions on those? And I think, here's one more. For every gas, what we just said, the most probable velocity is at the peak. The average velocity is a little bit to the right of that, meaning greater than that, and root mean squared is even greater than that. As the temperature rises, these three speeds shift to the right. All of them do, but they also shift in their separation to the right. The total area under the curve of the graph equals the total number of molecules. All that was on the other graph pretty much. And that is the end of topic 10. At the end of 10, you have a summary. 10.1 goes over some of the definitions. In 10.1, some of the temperature definitions and scales and things like this. In 10.2, with a couple of formulas there. Not all of them, but a couple of them. 10.3, the summary, has several formulas you use: coefficient of linear expansion, area expansion, and volume expansion. And they're very similar to one another, and they have delta capital T's, not the little t's like the slides did. Ideal gas law is 10.4. You have the definition, some of the numbers, and a formula or two. Kinetic theory of gases, the pressure of n molecules of an ideal gas contained in a volume V is given by P is equal to 2/3 nRT. So that couple of formulas there, actually 4 formulas there in 10.5. Conceptual questions, you have 14 there. The odd numbers have answers in the back, so you're welcome to do those. The problems, though, these are going to be more similar to what you see on your test. So any of the odds 1 through 9 would be from 10.1 and 10.2. From 10.3, thermal expansion of solids and liquids, that's odds 11 through 27, quite a few there. 10.4, ideal gas law, odds 29 through 39, so a fair number there. Kinetic theory of gases, odds 41 to 49. Then you have additional problems, and you can work any of these, combine all those pretty much, and that's odds 51 through 67. Okay. Now, since we did finish the chapter, I will go on and give you the test for this chapter. Now this is numbered test 8. I don't know if that matches the numbering that we've been following. I just can't say for sure. Okay, I'm going to turn this off and say on the above here. So this is your topic. What was this? 10, topic 10, test. And the other folks don't have as much time to work on it. Too bad. They probably shouldn't have left early. Am I feeling sympathetic? Not really. Okay. I have your labs made up. We don't have time for labs today, but basically we're going to do these on Monday. Okay? What's that? Oh, I can't.
I said okay.
All right. Glad you approve. Okay? We will do this on Monday. Okay? And that's about all for now. I was thinking we wouldn't finish this chapter until Monday, and I would finish it on Monday and give you the test then. So the sad news is, once we do the lab on Monday, and if you have anything, oh, and by the way, let me say this again too, in case any of you came in late. The student course evaluations are out there. Do any of you not know how to access those? Have you checked your email, the Washington State email that has a link to them? If not, go to the Washington State website, and when you get to the home page of Washington State, across the top of that page are a series of blue tabs. Near the right-hand side is a big gold tab that stands out there, and it says Quick Links, right? Okay, click on Quick Links, and you'll get a huge menu over here. You probably have to scroll down, and somewhere you'll finally see, and it either says Student Course Evaluation, Smarty Valves, something like that. I think it says Student Course Evaluation. Look for something that looks like that, and when you get to it, if it says Smarty Valves, you got it. How do you log on? Use your Lawson State ID number. I believe most of you, the folks that are transient students, will probably be a 1, 2 something, and then 1, 2, and 5 more digits. Those Lawson State students, you'll probably have smaller numbers than that, 119 or 111, yeah, wherever. Okay. Your password is your birth date, I believe, isn't it? 6-digit birthday. 2-digit month, 2-digit day, 2-digit year. I think that's how it goes. The screen will have it for you. It'll have a prompt to tell you what to do. So put in your birth date. And then, have any of you done the evals yet? You have. How long did it take you to do it? 5 minutes probably at the most. What's that? You did too. Did they, say again? Yeah. Did they do any additional things like registration, library, you just had the student course evaluation, and that's all. In the fall and spring, they usually ask for some others, so these won't take you long at all. Please, please do these. We do value them. We use them to monitor ourselves, and I use them to monitor my instructors that work under me. So please do your student course evaluations. All right? Any questions? Yeah.
Can I go ahead and get the final? Because I'll be here.
This is the final.
This one is the final?
That's the final.
Okay, good.
Yeah. I had figured that we weren't going to finish the chapter today, and I'd be passing this out Monday. But since y'all stayed, you get an extra weekend to work on it. There are some benefits for doing right. Okay? All right, good deal. That's all I got for today, unless y'all got any more questions. Okay. Then we'll see you on Monday, and we'll have the lab on Monday, and that will be pretty much it. Now, here's something else. Sorry, Ryan, you still there? I don't know if y'all can speak for the whole class, but since we aren't going to have enough to fill the whole day on Monday, Would you like to have pizza? Yay, nay, or what? Be okay? Now, with a class of 20, how many pizzas do you think that would be? Second? I can't hear.
It depends on where you get it from.
Okay, probably Little Caesars. That's the closest place that I have to. They'll be large. Submit.
How many people did you say?
There's about 20 in the class. There's technically 22, but one hasn't been here. She's sending her stuff in remotely. She's had a lot of medical issues. And then there's others that don't show up at noon anyway. What's your figure? How many pizzas do you think you would want to eat? 2, 3, 4, huh?
We might need about 8 boxes.
About 8 pies?
So everybody.
Okay, y'all have any dietary restrictions? Any preferences? Y'all go.
Probably not dealing with people with dietary,
Okay.
I'll eat too.
Good deal.
And this is my paper.
Okay, I don't need to fold it all.
Oh, okay.
Okay, so do you have any preference on types of pizza?
I think pepperoni.
Pepperoni,
Maybe it's a
cheese.
general idea for 2 types of people. But pepperoni is pretty neutral.
I'm sorry?
The taste.
The chapter 6 test.
Yeah. Oh, okay. Okay. So did I hear just pepperoni and cheese?
Yeah.
Okay.
Some people are picky about
And how many did you wind up saying? 5 or 6? 5. So 3 pepperonis, 2 cheeses. Sound okay?
That should be cool.
Okay.
Maybe you should keep it for the end of class and see how many people.
Okay. All righty. We'll see you on Monday. Okay. Let me try not to mess anything up. Okay, here, I think I messed. So I need to be. And I will be returning all these papers to you, so any quizzes and tests that have not been turned in, I'm not going to get them. Okay. Was it this test 7?
6, I believe. I don't know. Yeah, that looks good.
Okay. Do you think you don't have 6?
Let me see what 6 says. I don't remember.
I'm thinking it's not 6, so I don't have any copies left. That's the momentum.
Oh, no, I've done that. Yes.
Yeah.
That's,
And I told you about my situation on Monday. So, is there any way I could just get the lab early?
Yeah, you can get the lab right now.
Is there anything I could figure out, or is it something that we actually have to do?
You pretty much have to do it. Will you be able to listen to it on
Yeah.
YouTube video
Mm-hmm.
and then send it to me? But I'll need to receive it.
Can I send it to you by email? Like
Yeah.
scan it and send it to you?
Yeah, and scan it in PDF will be
I
best.
can send it to you by Monday. I can send it to you on Monday. I just won't be here.
Well, but you won't be able to hear YouTube.
So when will you
later
put it
on.
on there?
Huh?
When can you put it on there?
Well, we're going to do it in class on
Right.
Monday. So it'll be uploaded sometime Monday afternoon.
Okay.
And then
Maybe Monday evening. I'm going going to the airport Tuesday at like 6 a.m. and we're going out of the country. So,
Oh, you're going out of the country?
Yeah.
So you may not be able to do
I mean, I'll have there'll be Wi-Fi there, so
Okay.
I might, but I don't know if I'll be able to scan it. I won't have a printer there.
Oh, I see.
That's the thing.
Okay.
I have a scanning app on my phone, but I don't know how well that works.
Okay.
I'm
I
gonna try
can't
to
take
do
a
it Monday
JPEG file. You can take pictures of it
and
and send
send
it.
it. I can do that.
Does
Definitely.
that be easier?
I can do that by email. Yeah.
Okay. Then do that. I can't. My computer in my office won't do JPEGs, but I can get someone else to print them for me, and then I can break it.
Okay. And on Monday, I can still come. I can just come early and bring you my final,
Right.
and I can bring you. Oh, I can't bring you this.
Right.
I can bring you my final for this class and final for 202.
Okay.
And one more question. I kept on walking out because I brought my paper and I just read it and I wrote 201 on both of the papers.
Okay.
And then on one of them I had 2 typos. So I wanted to reprint them out.
Right.
and they want me to make a lost in state ID. I never made one of those, and I'm leaving after Monday, so there's just no point paying for all that. So do you know anywhere else I could print it out without me going back home?
Okay. I want to go down and finish eating right now, but after the next class, there will be time that you can do it in my office if you can't get anywhere else. The library also, I think. Oh,
That's where I went, and they wanted me to print out,
Okay.
Are we having a lab next class?
What's that?
We're having a lab next class.
I think so, yeah.
I mean, I'll be here the entire time.
Okay.
But, so you just want me to wait till after?
Yeah, because I really need to eat something before
Okay.
the next class. Well, now it's already time for the next class.
It'll
Thought I
be-
was letting
we'll
y'all
have
go for a little bit early so I could get down there.
I'm
but
going
it
to go get
doesn't
something
affect-
to eat too, and I'll be
Okay.
back.
Okay.
Everyone comes in a little late, so
Right.
you'll have time. Okay. Thank you for working with me. I'm sorry.
All right. No problem.
And after the lab today in 202, would that be the last lab?
I'll have to think on that. I'm having trouble keeping up with what everything is right now, so I'll have to get my head around that one a little bit. I'm just messing things up now, I think. Where am I? That's all right. Now, there. Okay, good. I was afraid I'd screwed that up. Oh, goodness gracious, I didn't upload this.